So now that we have studied binary search tree, now it is a right time to ask a problem with binary search tree. So what do you think? What can be wrong with the binary search tree? What may go wrong? So a binary search tree could be skewed, which means that a binary search tree could look like this also, or maybe this could be left skewed or right skewed, right? Or maybe some mix of this, right? Maybe like it will be skewed like this, right? Something like this, which means the height of binary search tree could be as good as number of nodes, which is not a good thing, because a binary search tree will be just working like a linked list, right? So it is not a good thing. So let's make BST efficient. But how can we make a binary search tree efficient? So BST can be skewed, this is our observation, and how can we make the binary search tree as efficient? So we need a balance condition that ensures that height is always log n. Okay, so you got the problem is that binary search tree can be skewed. Solution is that we need something that makes sure the height is always order of log n. Okay, now what do you think that what should I impose as a condition such that the height is always order of log n? Let's see some suggestions. So suggestion 1, which says that right and left subtree of the root have equal number of nodes, which means they are saying that for the root, if right and left subtree both are having equal number of nodes, then maybe things will be fine, right? If both are having equal number of nodes for the root, this is the root, and if left subtree and right subtree, this is the left subtree, this is right subtree, if both are having equal number of nodes, then maybe the height is always log n. Can I say like this? Just think about it. Answer is no. Why? See this counter example. See here, the height of left subtree and the nodes in the left subtree, which are 1 2 3 4 5 6 7, there are 7 nodes here and 7 nodes are here only, right? So nodes in the left subtree and nodes in the right subtree both are same, which are 7 and 7. Still height of this is not log n, right? It is some in proportion of n, maybe n by 2 or something like this, right? So this suggestion 1 seemed good, but it is not a good criteria to make height log n. See, we wanted to make a height log n, but if we go for the suggestion 1, then there could be some trees which are like this, which says that for the root left subtree and right subtree both are having equal number of nodes. Still there is a problem, because the height is not yet log n. Now let's go for some other suggestion. This suggestion is saying that right and left subtree of the root have equal number of nodes and equal height also. So earlier I was having just equal number of nodes, right? Now I will be having equal height also. You're getting? So for the root, whatever is there on the left subtree, whatever is there on the right subtree, they just not have equal number of nodes. See, earlier what was the problem? They were having equal number of nodes. But if I also say that they should also be having equal height, then maybe things will be fine. Which means that if I impose the equal height also, apart from the equal number of nodes, then this is have to be like this skewed have to be of the same height. Then you can say that if you are imposing these both conditions, then you can say then always the height will be log n. Is it true? Just think about it. So if I make this kind of condition, then will I be able to make the height as order of log n always? Apart from equal number of nodes, I also say that equal height is also necessary. Then answer is no. Can you think of counter example which follow both of these conditions, still height is not order of log n? Yes, it is, I think, easy. If you can think of it, it is good. Otherwise, let's just see this counter example. See here, the height here and the nodes here. So height is 1 2 3 4, right? So height is 4 in the left subtree, and nodes are 1 2 3 4 5, and nodes are 5, right? So heights and node both are same here and here, right? Here also height is 4, nodes are 5. Here also height is 4, nodes are 5. So for the root, the equal number of nodes are there in the left subtree, equal number of nodes are there in the right subtree, and equal height is also there. Then also this is not having order of log n as the total height, right? So I hope you got it. So that's why the suggestion 2 is also not useful. Let's go for some other suggestion. So the suggestion 3 is saying right and left subtree of every node, not just root, every node should be having equal number of nodes. So they are saying for every node, right and left subtree should be having equal number of nodes. So whenever you are adding one here, you also need to add one here. But here this is just one and this is 0. So you cannot add one here because this will just violate the property, right? So for every node, left subtree and right subtree should be having equal number of nodes. So that is why like this is the perfect tree which is following this, right? So the height is order of log n, that is okay. But can you think of some counter example again? Just think about it, that height of number of nodes in left subtree and right subtree for every node, not just root, for every node should be same. So which means if you just start with, then just make 1 after that. If you just want to add some node, then you can't just add here because the height the number of nodes here in the left subtree for this node are just 1 and on the right subtree it is 0. So that's why you need to add 2, and if you are adding 2 here, then you should be adding 2 here also because of this root violation, right? Root will be otherwise having more number of nodes in the left and less number of nodes in the right. So I think this is good. So what is the counter example? Actually there is no counter example for this. I mean, this is a perfect condition. So this condition is perfect, right? So this condition will always make sure that height is order of log n. In fact, not just order of log n, it will be exactly equal to log n. Okay, I mean there won't be constants also. So is this a good condition? Just think about it. No. Why? Because this condition is good. I mean this condition will make sure that height will be order of log n, but it is too strong condition. Only true for perfect trees. Only true whenever you are having all labels as full. So this condition is good, there is no problem in this condition, but it is too much strict. I mean I have to go for the perfect trees if I am following this condition, right? I mean this condition is okay to give you log n height, order of log n height, but it is too much strong. I want to have some lighter condition which gives me order of log n height, and also like my condition should not be too strong. Okay, so that is given by a balance condition. So balance condition in AVL tree says that balance of every node is between -1 and 1. That means balance of every node will be either -1, 0 or +1. So how to find out the balance of any node? I will just say balance of node equal to height of left subtree and minus height of right subtree. So if this balance condition for every node, if it is satisfied that every node balance is either -1, 0 or +1, then I will say that it is an AVL tree. I mean AVL tree have to be a binary search tree first of all. Okay, so AVL tree cannot be a random tree, it has to be binary search tree. And then on top of this, because I am improving binary search tree, on top of this I will say that it should also follow the balance condition. And what is the balance condition? It says that for every node balance will be either -1, 0 or +1. And how to find out the balance? I will use this formula which says left minus right height. Let's just see whether this tree is AVL tree or not. So first thing to check here is that whether it is a binary search tree or not. Just check all lesser than 6, all lesser than 4, greater than 6, and then you should be having here you should be having between 6 and 8. So yes, between 6 and 8, and here you should be having between 8 and 11, which is 10. I think yes, this is a binary search tree. There is no problem in that, right? So this is a binary search tree. First of all, you need to check whether it is a binary search tree or not, and then go for the balance condition. For the leaf, it is left minus right height. So for the leaf, the balance factor, this is called balance factor. So I will be saying BF for short. Okay, balance factor. So for the leaf, it is 0, 0, 0, 0. And then for internal nodes, you can say left height is 1, right height is 0. So 1 minus 0, which is 1, right? So you can also do 0 minus 1, 1 minus 0, does not matter. Okay, you should be either end up with 0, 1 or -1. Okay, so left minus right or right minus left does not matter. I am defining it as a left minus right, that's okay. Okay, so for here it is 0 because left height and right height are same. For here it is 1 minus 2, which means -1. For here it is 2 minus 3, right? So 2 minus 3 is again -1. So yes, it is a BST. It is a BST, and balance factor is always for every node is also between -1, 0 and 1. So both conditions are satisfied. That's why I will say that this is an AVL tree. This is a perfect AVL tree. There is no problem in that, right? Now let's go to some other example. Tell me whether it is an AVL tree. Let's just first check whether it is a binary search tree or not. To check that, I will say that okay, everything lesser than 6, now everything lesser than 1, everything greater than 4 and lesser than 6, right? So between 4 and 6 should be there. Yes, that is true. And then greater than 1 and greater than 1 lesser than 4, right? Greater than 1 lesser than 4, okay. And then lesser than 3 and greater than 1. Yes, this part is okay. And here yeah, I think this part is also okay. Yeah, this is a binary search tree, no problem with that. What about balance factors? So this is having 0 0 0 0 as balance factor. Now what about the balance factor of this? This is having 1 as a balance factor because left minus right. What about balance factor of this? This is having 0, which is a left subtree height, minus 2, 0 minus 2, which is minus 2. So balance factor of this node, I do not need to check all the nodes, okay, just one violation is enough. So balance factor of this node is not either minus 1, 0 or plus 1, right? Is neither minus 1, 0 or plus 1. So that's why I will say it is not an AVL tree, not an AVL tree. I hope you got it, right? It is very easy to check. First check whether it is a binary search tree or not, and then check whether the valence factor is satisfied for every node, okay? If even you find one violation, you will say that it is not an AVL tree. Now tell me whether this is an AVL tree. So here 3 lesser than, yes, it is a binary search tree, binary search tree, binary search tree. Yes, I think it is a binary search tree. So binary search tree, yes, it is a binary search tree. What about balance factors? So here it is 0 0, then you will say it is minus 1 1, does not matter, okay? And this is 1, then you will say yeah, this is not balanced, right? Why? Because left height is 0, right height is 2, so it is minus 2. That is why it is not AVL tree. AVL tree is no, and binary search tree yes. Why? Because balance factor of this node is not satisfied. Should I need to check balance factor for 3? No, just one violation is enough, right? If it is minus 2 as a balance factor, I will say I can stop and I can declare this to be not an AVL tree. Okay, so this is how we can identify whether some tree is AVL tree or not, right? And now we know the motivation for the AVL tree. Now let's go for the proper insertion and operations, like some other operations of the AVL tree in the next video. Now let us start with few operations on AVL tree. But before that, let me show you that how does a struct node in AVL tree looks like. So if you remember from binary tree or binary search tree, then it looks like this, which means that it has one data, left pointer and right pointer, right? It has 3 fields in binary tree. So it is also a binary tree. I mean, AVL tree is also a binary tree, but here I will be storing one more field. Can you guess what? So what is the difference between binary search tree and AVL tree? AVL tree is a height balance tree, right? So can you tell me that what is the extra field that I need to store in a struct node? Yeah, balance factor, right? So I need to store balance factor of every node, right? But instead of storing the balance factor, I will be storing the height. This way, like, it will be easy for the operations. So what I will be doing, I will be storing the height. And now I will show you that how to operate on binary operate on AVL tree, which means insertion, deletion and these all. So once this theoretical part is over, I will also show you that how to do it in the code, where I will be using this this fourth field, which is height, to calculate the balance factor. Okay, so let me first do some example for the insertion and then I will show you the code. Okay, so in this video we will just keep a theoretical introduction to the insertion. So there are like 3 operations that are possible. One is search, which is exactly same as binary search tree, which means like if you want to search something in AVL tree, then you can do that in the similar way as binary as the AVL tree, right? So let me go to the insertion, AVL tree insertion. Now let's do one thing, that let me take a mini example. So AVL tree insertion is basically binary search tree insertion, plus there will be something balancing, okay? Some kind of balancing will also be happening in case of insertion. Let's just see this. Suppose I want to insert 3, then 2, then 1. To insert 3 there is nothing, because like initially it is an empty tree, and then 2. So 2 is smaller than 3, so I can easily insert. But this is not all. So after every insertion, I have to check whether the tree is balanced or not. So currently it is balanced because the height of the left subtree is 1 and then the right subtree is nothing. So 1 minus 0 is 1. So balance factor is 1. So there is no problem. Now insert 1. After inserting 1, always start from the newly inserted node. Okay. So after inserting 1, check which node is getting imbalance. So always start from the newly inserted node, which is 1. Now if you start from 1, you will say that okay, 2 is balanced because it is 1 minus 0. And then what about 3? Yeah, 3 is unbalanced because it is 2. Left subtree height is 2 and right subtree is nothing. So this is first imbalance that we are seeing in case of insertion, right? So I hope you got it, that 3 is imbalanced after inserting 1. But we will not stop it here, like just saying that it is imbalanced, our job is not done. We will make this tree balanced. So how I'm going to do it? I'm going to convert this into another tree such that the tree is balanced. So something like this, okay? Now, suppose if I give you this structure and if I say that these are the 3 values, 1, 2, 3, that you need to fill these 3 values in this structure, what you will be doing? You can easily fill, right? How many such combination permutation in these things are possible? Just one. Given any structure, if you are asked to fill a binary search tree or a AVL tree, right? So then it is only one possibility. Why? Because see, here you will be writing the minimum and then next minimum and then next minimum, because in order traversal has to be unique, right? So that is why you will say that here only minimum will come, which is 1, and then next minimum and then next minimum or maximum, which is 3. So only one possibility is there, right? And always one possibility given any structure, I mean like any maybe like this, okay? Given any structure, like if they ask you to fill this binary search tree with some values 1 2 3 4 5 6 7, if they ask you to fill with 7 values, maybe 1 2 3 4 5 6 7, then there is only one possibility. You will say that minimum will come here, which is 1, so minimum will come here, and then next minimum, which is 2, will come here, and then you will say that okay, after that you need to actually check like which is you need to actually do the in-order traversal, right? So I have not made this tree properly, but that's okay. I think after that this will come, right? This will come, and then this whole thing is on the right, and then I think this will come, right? This will come, and then this will come, this will come, and this will come, right? So you will say 1 will come here, 2 will come here, 3 will come here, 4 will come here, 5 will come here, 6 will come here, 7 will come here. That is how you can fill this structure uniquely, okay? And there is no other possibility. So given this structure, you will say that 1 2 3, like this kind of possibility is there only, okay? And then this is called rotation actually, okay? This is called single rotation, but I will not go with these terminology. I will tell you later, but for now let's keep it very simple. This is called rotation. Now here if you observe that this thing was looking like an stick. A stick means just like your daily routine stick, okay? So it is looking like an stick. So I will call this as an stick. So I will say this is an stick, and this is looking like just like a mountain, right? Just like a mountain. So I will say that this is mountain. This is mountain. So this structure I will say mountain, and this structure I will say stick. So I am saying that I want to convert from stick to mountain. Okay. So whenever I have a stick, I will convert that to mountain. I hope that is okay to everyone. Okay. So now to convert that to mountain, there is only one possibility. I mean, there are it is not like that multiple mountains are possible or like that. Okay. There is only one mountain that will be possible. Now, like let me go with this next example, which is inserting 5, 10 and 15. So if I insert 5, nothing, and then if I insert 10, so you will insert at the right. Now check the balance factors. So I think everything is cool till now. Now insert 15. Now you will say 5 got imbalance. This is the first imbalance, right? So you will say that okay, go from inserted leaf, like you will always check from the inserted node, and first node that got imbalanced from this to root is 5, right? 15 is not imbalanced, 10 is not imbalanced, then 5 is imbalanced. Then that's okay. You will again say that this is one kind of one kind of form, that again you want to convert that to a mountain, okay? And then if I ask you that can you fill these 3 spots, then you can easily fill. How? Just write the minimum value here, which is 5, and then 10, and then 15, right? Very easy, right? This is very, very easy. Now you will say that this is also a stick, okay? This is also a stick, and which I want to convert into a mountain. This is again a mountain. So what I'm saying here, that either you have this kind of stick, I mean either you have this stick or this stick, does not matter to me. I will always go to the mountain, okay? I will always go to the mountain. I hope that's okay. Either you have this or you have this, you just draw a mountain out of this, and that's very easy, okay? Now let me just do one thing. Let me label all of this these nodes. Let me say that this is X, okay? let me say that this particular node is x, this is y, this is z. Okay, and then if this is x, y, z, so you can also say here that this 2 was y, and then this 1 is x, okay, 1 is z, and then 3 is x. Okay, you can also say on the mountain. So why I am annotating this, you will get to know very soon. So basically annotation is sometimes useful, that's why I'm annotating, just for our sake of practice. Okay, so you can just annotate x, y, z here also, x, y, z, and then you can say 5 is x, and then 10 is y, and 15 is z. Okay, this is z. That is how you can annotate all of this trees, right? I hope you got it. Now for this stick, as you are seeing, as you are seeing here in this example, also, so once you annotate x, y, z, okay, then after that you notice that y is always on the top of the mountain. Okay, y is always on the top of the mountain. If you can remember this, then it will be very easy to to draw a mountain. Otherwise there is no need to remember this. I mean, if you have this in your subconscious mind, then it is okay, otherwise there is no problem. I mean, what I'm saying, that suppose in future you get some stick like this 10 and then maybe 8 and then maybe 3, something like this. Okay, suppose you get some stick like this and you want to convert that stick to a mountain, then again and again, I do not want you to again and again figure out that okay, here 3 will be there, here this is 8. Okay, this number is 8. So you do not need to again and again see that okay, 3 is here, 8 is here, 10 is here. If you can just annotate like this with x, y, z, then you always remember that from the stick, this middle portion, which is y, always goes to the top, and then 3 should be smaller than 8, then x will be here and z will be here. Actually x and z are not much important, y is important. I mean, if you remember this in your subconscious mind, it is okay. Otherwise we can easily, like in just a fraction of a second, we can easily figure out that 8 will come where, or 3 will come where, or 10 will come where, right? So if you can remember this, that this y comes on the top in case of stick, then it is okay. Otherwise there is no problem. I'm just saying that if you by chance remember this in your subconscious mind. Okay, so I hope that is fine. Now let me convert this stick into a mountain. Can you convert it? Very easily. Just annotate it x, y, z. Now you may be asking me why I'm annotating it with x, y, z. I will answer this question little later. Actually there is no need of annotation at all. At any place there is no need of annotation. It is just for my sake of understanding I am doing it. So don't think that I'm complicating it. Actually for the big examples, if you annotate, then it will come little bit easy. Otherwise there is no problem, you do not need to annotate. Okay, so let me just annotate it, and we will practice with the annotation. Otherwise there is no problem. So you know in your subconscious mind, if you know that okay, by will come on the top, which means 25 will come on the top, then it is okay. Otherwise there is no problem, you can easily figure out that which will come on the top, which will come where, right? And then 13 is lesser than 25, that's why it will be here, 38 will be here. So I can easily convert this stick to a mountain, right? This is a mountain. Now can you convert this stick to a mountain? See, this is again a stick. Can you convert this stick to a mountain? Very easily. Like let me just do x, y, z, and you know that y will come on the top, which is 84, then lesser than 84, which is 51, will come here, and greater than 84, which is 89, will come here, right? So this is y, this is x, this is z. If you want, you can annotate. If you do not want, you do not annotate. Okay, like I will just say that for the sake of practice, annotate it, it won't take much time. Okay, now let me do another examples. Okay, so 2 examples we have already done, which is inserting this 3, 2, 1, 5, 10, 15, like that. Now I'm currently doing short example, then I will go to very big example. Okay, so let me insert 3, 10 and 20. 30, 10 and 20. So after 30 it will be just like this, and then 10 is smaller than 30, it will be like this, and then 20 is smaller than 30 but greater than 10, so it will be like this, right? After inserting 20, just check whether the things are imbalanced. So you will say that okay, 20 is not imbalanced, 10 is also not imbalanced, but 30 is imbalanced, right? Now, so you found out that 30 is imbalanced, and these are the 3 nodes, right? So just convert that also to a mountain. It is not a stick, that is okay. So let's just convert that also to a mountain. Now here you will be writing the minimum, here you will be writing the second minimum, here you will be writing the third minimum or the maximum, whatever you want to say. So you can convert that to also a mountain, right? Very easy. So there will be a unique mountain. It's not like you can have multiple mountains like that. Okay, so earlier it was a stick. Here also I will be calling it with some name, just for our sake of convenience. I will be calling it an elbow. It looks like an elbow, so I will be calling it elbow. See, these are not actually standard terms. These are just for the sake of explanation, I am calling it stick, elbow, mountain, but that's okay. Okay, so this is a mountain. Now you know what to do, right? If given a elbow or given a stick, what is my goal? My goal is to always reach to mountain, right? Now let me annotate these nodes also. Let me say this is x, this is y, this is z. Now 20 is z, right? 20 is z, y, this 10 is y, and 30 is x, right? So you can annotate both the trees. So this is z, this is y, this is x, right? Now let me just insert this 4, 8 and 6 also. So 4, after that 8, after that you will be having 6. Now again you see this is imbalanced, right? 4 is imbalanced, so you will say that this is also an elbow, right? This is also an elbow, and you will convert this elbow to a mountain. How? Very easily. You first draw the mountain, and then you know that minimum will come here, minimum is 4, and then middle one will come here, then 8 will come here. So can you just annotate it very quickly? We can do it. I think we can do it. This is x, y, z, and x is 4 and z is 6, okay, and 8 is y, right? So you can annotate if you want, like if you do not want, you do not annotate, like that's okay. Okay, this is again a mountain. Okay, so you can convert either elbow to a mountain or stick to a mountain. Now we know that, right? So there is a little difference between converting elbow to a mountain and stick to a mountain. I mean, difference of annotation basically. In case of stick, the top element was y, if you remember, but here the top element is z. I mean, if you are annotating, then you can remember these things subconsciously in your mind. Otherwise, there is no problem, right? I mean, given an elbow, you can easily convert to a mountain, even though you do not remember whether z will come on the top or y will come on the top. These things won't matter. But if you remember subconsciously, it is okay. Like you can remember that, okay, in case of elbow, z will come on the top. Okay, in case of stick, y will come on the top. So now let's just convert this elbow to a mountain. Can you do it? I think that's also very easy. How? Like if you remember, then it is okay. Again, I'm saying that if you remember that this is z, right? So first annotate, okay? First annotate, then only rotate. So rotate means like convert that to a mountain. First annotate. Now after annotation, like if you remember subconsciously that 25 will come on the top, then it is okay. Otherwise you can easily figure out that who will come on the top, okay? And then 25 lesser than 13, and then 38 will come here, right? So this is z, this is y, this is x. That is how I can convert this elbow to a mountain. Okay. Now similarly, you can convert this elbow to a mountain. If you can just remember that, okay, z comes on the top, then it is okay. Otherwise also things are fine, right? This is 9, this is 12. This is how you can convert this elbow to a mountain. This is again a mountain. I hope that is fine to everyone, right? So now we know that how to convert a stick to mountain, how to convert an elbow to mountain, right? How to convert a stick to mountain, elbow to mountain. This is basic building block. Once you know this, I mean, actually this is extremely easy, but once you know this, you know how to rotate and how to do insertion in the AVL tree. So once you know this, things are very much fine. So this is basic building block. Okay, this is extremely important. Now there are few terms that I would like to introduce. One term is called rotation. I mean left rotation, right rotation. So basically whenever I am doing stick rotation to a mountain, it is called left or right rotation. It is called actually single rotation. So single rotation means I am converting a stick to a mountain. Okay. So here let me write it. These things are called, if I am converting a stick to a mountain, this is called single rotation. Single rotation. I mean, this is just a term. If you want, you can remember it. Otherwise, there is no need to remember whether it is single, double, these things. Okay, like if you remember, it is okay. Like converting a stick to a mountain called single rotation. Converting an elbow to a mountain called double rotation. Double rotation. Okay. Now, why it is called single and why it is called double? Because in case of in case of stick to a mountain, I mean, it is not like a mechanical rotation that you have some stick and you are like, okay, let me just rotate it. It's not like that. These are the pointers. Okay, these are the pointers which you will just manipulate. So basically, here in case of single rotation, we are just manipulating one pointer. I think one or two pointers. Maybe I'm just saying that two right should be pointing to whatever is pointing to two, right? I mean, two right should be pointing to 3, like that. I can just do that. So it is called a single rotation. Basically, these are the terms. Now if it is this kind of stick, it is called left single rotation, left rotation. So it is called left rotation. Okay. If it is this kind of stick, it is called right rotation, RR rotation. So this is called LL rotation, this is called RR rotation. These are just terms. If you want, you can remember it. Otherwise, we will just say that stick to a mountain, LO to a mountain. That is all. Okay. I will stick to this terminology. I will say stick to a mountain, LO to a mountain. I will not say LL, LR or these things. Okay. So I will not go into these terminology again and again. I'm just telling you for the sake of completion. Otherwise, we don't need it. Okay. Now, in case of elbow, it is called double rotation, and here this is called, this kind of elbow is called LR. Okay, it is called left once you are going left and then right. So it is called LR rotation. LR rotation, and this is called RL rotation. RL rotation. Okay, so this is called LR rotation, this is called so first you are going right and then left, this is called RL rotation. Okay, and why it is called double rotation is because suppose you have some elbow, maybe something like this. Okay, you have some elbow, can you fill these values? I think minimum, let's just take some minimum value, which is, let's suppose 10 is coming here, and then you can say that okay, this is basically everything is on the left of this. So let me make it clearly just for the sake of explanation. So everything should be on the left of this, just to make it clearly. Okay, so after that, let me say this is 20 and let's say this is 30. Let's suppose this is one elbow you have and you want to convert that to a mountain. So it is called double rotation because in most of the cases, I mean, it depends on the way you are implementing. I will show you the implementation, don't worry. But in most of the cases, what we do, we first convert that to a stick. Okay, even though it is an elbow, instead of converting it to directly a mountain. So our goal is to reach to a mountain, right? Now, instead of converting directly to a mountain, what we do, we just exchange actually this 20 and 10. We just say, let me first convert that to a stick, which means I will just say like this. Let me just exchange this 10 and 20 and let me actually just convert this to a stick. Okay, so I will just do one rotation and then I will convert. I know how to convert from a stick to a mountain. Then I will convert from a stick to a mountain. Then I will say that okay, 20 will come on the top and then 10 and then 30. Okay, basically like in terms of coding you can understand, like actually in terms of coding, I will be having a function which is saying stick to mountain. Okay, I will be having a function which is stick to a mountain, and then let's suppose I have some function that does some pointer manipulation. Now whenever I want elbow to mountain, whenever I want elbow to mountain, then I will be doing what? I will be first, doing this kind of rotation. I will be first converting elbow to a stick. So I will be doing elbow to a stick, elbow to stick, and then I will be doing what? Stick to mountain. So basically, I will be calling this function itself. So I will say stick to mountain. I mean, I will show you the actual working codes, but for now, I'm just trying to explain you that this function, which means elbow to mountain, will be using stick to mountain internally. Okay, so in most of the cases it happens. So basically like if you want, you can without calling this function, you can directly convert, but that is okay. I mean, first I will be converting from elbow to stick, and then internally I will be converting stick to mountain. So like first I will be converting elbow to stick, and then internally I will be calling from stick to mountain, right? So that is okay. I mean, these kind of terminology I'm not going to again and again explain. Like I just wanted to tell you that this is called double rotation. Whenever you have elbow, it is called double rotation, but that is okay. I mean, I'm not going to again and again doing the will be doing the double rotation. What I will be doing, I will be reaching from here to here directly. I will not introduce this stick in between. I will say that okay, this is the elbow you have, tell me the mountain. Okay, I will say that this is the elbow you have, tell me the mountain. I will say this is the elbow you have, tell me the mountain. I will not say okay, first convert that to stick, then go to the mountain. No, why to waste so much of time, right? When you have elbow, you know how to reach to mountain. That is very easy. Why you are wasting your time to first convert that elbow to stick, then stick to mountain? There is no need. There is absolutely no need. Okay, but for the sake of completion, I just told you that yeah, this is called double rotation and all. Okay, now I hope you got it. Now whenever I say rotation, it does not mean a mechanical rotation. It's not like okay, this is one rotation. So now if I'm moving from this from here to here, this is okay, this is one rotation. And then if I'm moving this from here to here, this is another rotation. No, it is not a mechanical rotation. It is just a pointer manipulation. Okay, rotation. So rotation does not mean this in case of AVL tree. I mean, some student actually says that can we first rotate it like this and then rotate like this or whatever, right? So it is not a manual rotation or something. This is just a pointer manipulation. Okay, so rotation means here pointer manipulation. Pointer manipulation. It is not like a mechanical rotation like this. Okay, so I hope you got it. Now let me go to a big example where I will be inserting some sequence of nodes. So with this example, your every of your confusion about the rotation and these things, everything will get clear. And we are going to build a huge AVL tree for this insertion order. Let's just do it step by step. 10 is very easy, and then 85. Go to the right of 10. Then 15. Go to the right of 10 and left of 85. Now you know that this is imbalanced. What is this? Is this stick or elbow? Very easy to answer. What is this? This is elbow. So let me first annotate. I mean, if you want, you can skip the annotation, but my suggestion is that just annotate it, okay? And then convert that to a mountain. So in case of elbow, if you remember, then it is good that Z comes on the top. Otherwise, also you can easily figure out, right? So this is 10, this is 85, this is Z, right? Now this is Z, this is X, this is Y, okay? So I think 10 is over, 85 is over, 15 is over. What about 70? Let me just insert 70. 70 means 15 greater and 85 lesser. So 70, after inserting 70, I don't think there is any imbalance. So 70 is also over. What about 20? So let me insert 20, 15 greater, 85 lesser, 70 lesser, right? So after inserting 20, so let me just remove this annotation now, because it is not useful, because I will be doing the annotation again for the different imbalance. So after inserting 20, you see that is this a balance or imbalance. So start from 20 and go to the root, okay? So 20 is balance, okay? 70 is also balance, but 85 is imbalance. Since 85 is imbalance, this is the first node which is imbalanced, right? Now from this to a newly inserted node, just go to that path and find out whether it is stick or elbow. So this is an stick. Why? Because from the first imbalance node to the leaf, it is to the newly inserted node, basically first imbalance to the newly inserted node. So this is an elbow. Very easy to figure out, right? Now if you want, you can annotate, but for now I'm not doing it. Okay, I mean, you should be doing it actually, so let me also do it. Okay, let me say, before rotation, let me say this is X, this is Y, this is Z. Okay, now if you can remember that in case of elbow, Y comes on the top, then it is okay. Otherwise also you can do it, right? So it is 20 and then this is 85, right? So now I am done with 20 also, right? Now insert 60. So before I insert 60, let me do one thing. Let me go to the next page. Let me go to the next page and let me basically erase some of this so that I can insert 20 here only. Okay. So let me remove this. And now I can insert 20. So to insert 20, what I will be doing, I will go to the right of 15 and then I will say that, okay, 20 is inserted, 60, about 60. So I will go to the right of 15 and then I will say, okay, lesser than 70 and then greater than 20. So 60 will get inserted here, right? Now let's just check whether things are balanced. So 20 is balanced and then 70 is also balanced because 2 minus 1, it is balanced. And now 15, okay, 15 is imbalanced. That is good, which means like it is 1 minus 1, 2, 3, right? Right subtree height is 3. So 15 is imbalanced. Now the question is that whether this 15 should be making an elbow or the stick, which means should I be saying that this forms an elbow, or should I be saying that this forms an stick? I mean, I will be doing like this, or I will be doing like this. So should I be saying that this is an elbow, or I should be saying this is a stick? This is a stick or elbow. What do you think? So see, 15 is imbalanced. Now to determine whether it is an stick or elbow, what I will be doing, I will go to the node by which it got imbalance, right? After inserting 60 only it got imbalance. So I will go from 15 to 60. So if you go from 15 to 60, then you will be saying that it is an elbow. It is not a stick. Why? Because this is forming an elbow. If you go from 15 to 60, it is forming an elbow, right? So to identify elbow and stick, it is also like it is also necessary to identify elbow and stick. And to do that, you just go to the node by which it got inserted, like the newly inserted node, basically. Okay. So now you can convert this tree to a balanced tree. How? First annotate. Okay, now you will see that why I am saying annotate. So just annotate it first, and then you can easily convert this elbow to a mountain. If you remember that this 20 will come on the top, then it is okay. Otherwise also things are fine, right? 15 and then 70. Now let me annotate it here. This is Z, this is X, this is Y, right? Now let's just add all of these nodes which are remaining. how many nodes are remaining? Just 3 nodes, 10, 85 and 60. So let's just say that okay, 10 is on left of 15, so very easy to add 10. What about 85? 85 is right of 70. 85 is also very easy. What about 60? 60 is right of 20. Now you see on the right of 20 there is 70. So whenever like if I want to insert this 60, if I want to just adjust this 60, I will go to the 20, I will go to the right of it. So I encountered 70 or I encountered y, right? So I will say that okay, say this 60 is right of z, but if I go to the right of z, I found y, right? And there is no space on the right of z. So what I will do, I will take the help of y. I will say that okay, 60 is on the left of y, so I will insert it here. I will insert it. You're getting? See what I did. I first converted this elbow to a mountain very easily, right? This XYZ is an elbow to a mountain. Then these were the three nodes which got left: 85, 10, or 60, right? So to insert 85, it is very easy. That will be on the right of y, Inserting 10 is also easy. Left of x or left of 15, very easy. Inserting 60 got little tricky, which means I wanted to insert to right of z, but on the right of z I found y. So I will take the help of y. I will ask y that where should I be inserting this 60. It will say that okay, 60 should be on the left of me. So I will insert that on the left of it. Okay, that is how I can easily make the balance AVL tree or balance vanishing tree, which is an AVL tree. Right now, like if you ever get confused like whether you are doing it wrong or right, then you can just use your own intuition. That's this is 60 and 60 should be on the left of 70 only, right? So this 60 was only little tricky, otherwise everything was fine. Okay, so let me just complete this big example. It is actually a big example. So once I complete this big example, you will be getting much more intuition, and then I will give you one example, one such big example as an homework, and then you can try inserting on your own. Okay, 60 is over. Now let me insert 30. Now to insert 30, what I will be doing, I will go to 20, 70, 60 and then 30. Okay, now I will check whether it is balanced or imbalanced. This is 60 is balanced, 70 is also balanced, 2 minus 1, it is also balanced, 20 is 2 and this is 1, 2, 3, 20 is also balanced, no problem after inserting 30. So let me just cross out this 30. What about 50? So 50 will go here, then here, then here and then right of 30. Okay, 50 will go here. Now tell me whether things are balanced after inserting 50. No. Why? Because this 50 is balanced, okay, 30 is balanced, okay, but 60 is not balanced. So go from newly inserted node till root and to check whether things are balanced or not. Okay, so this 60 is the first node which was imbalanced, so I will start from 60 only. Now tell me whether it is an stick. So like actually I don't think stick is even an option, so it is an elbow only, right? Okay, now can you convert this elbow to a mountain? I think very easily we can convert. How? You can just say that this is elbow, and you can just say that we can convert that to a mountain. Okay, let me remove this part and let me basically shift it here only so that I can show you everything on the one page. So I just want to convert this elbow to a mountain. So everything else will remain as it is. So let me just make the copy of this, and I will just remove this part. And here, instead of this elbow, I will be attending the mountain. And how it is possible? Very easy. Like you can convert this elbow to a mountain. You will say that okay, 50 will be on the top, and then you will be having lesser than 50, which is 30, and then 60. If you want, you can annotate. Otherwise, let's just keep it simple. Okay, so 50 I just inserted. What about 65? You can easily insert 65 also. You can say that okay, go to the right of 20, go to the left of 70, go to the right of 50, go to the right of 65, 60. So let me just check whether things are balanced or imbalanced. So this is balanced, this is balanced, this is balanced, right? 2 minus 1. This is also balanced because 3 minus 1. Okay, this is not balanced. 1, 2, 3 minus 1. This is not balanced. So here Z is first imbalanced node, right? This is the old annotation. That's why I am removing it. Now you will say that Z is first and this 70 is first imbalanced node. So you can balance it. How? You will be first identifying whether it is stick or elbow. How to do it? You start from 70 and go till the newly inserted node, and then you will say that this is an elbow, right? So 3 nodes will come and you will say this is an elbow. Now can you convert this elbow to a mountain? Again, very easy. How? You just first annotate, like if things are little complicated, first annotate it, okay, using xyz, and then let's just convert this stick to a mountain, this elbow to a mountain. It is also very easy. Let me remove this portion and let me convert. So let me copy the edges part, which is this 20, 15 and 10, and let me just do one thing. Let me just convert this elbow to a mountain. So if you want to convert, then you know that Z is coming on the top. Like if you remember that, then it is okay. Otherwise also that is fine, right? So Z will come on the top, which means like 60 will come on the top. On left of it, 60 lesser, which is 50 will come, and on right of it 60 greater, which is 70 will come, right? So let me again annotate after the rotation, which means it will be Z, it is Y, it is X, right? Now let's do one thing. Let's just append all the remaining nodes. So how many nodes are remaining? I think this and this, 3 nodes are remaining, which is 30. So 30 is left of 50 or left of Y, which is okay, and then 65, which is right of 60. Okay, 60 right of 60 is something there. So I will actually do the 65 later. 85 is right of 70. 85 is easy. Now for the 65, I will go to the right of 60. On the right of 60, I found X, right? So I will take the help of X. So X is saying that 65 should be on the left of it, right? On the left of it. So just see here, on the left of it. And also using your own intuition, you know that it should be on the left of it, right? So 65 will be coming here. That is how very easily you can just rotate from here to here. And now it is balanced. So in case of insertion, you do not need to check again and again. Once you fix one imbalance, okay, you fix the imbalance here at the 70. Now you do not need to check again and again. In case of deletion, I will tell you this is little different, but in case of insertion, you just need to rotate it only one time, either stick to a mountain or elbow to mountain. After that, you will be 100% sure that your tree is balanced. Okay. Now 65 is inserted. What about 80? So to insert 80, I will go to the right of 20, I will go to the right of 70, I will go to the left of 85. So 80 will get inserted here. Now check things are balanced or not. I think this is 2 minus 1, it is balanced. 1, 2, 3, 1, 2, it is balanced. 1, 2, 3, 4, it is 2. Oh, 20 is imbalanced this time, right? This time 20 is imbalanced. This is 85. And now to balance 20, what I need to do? I first need to identify whether this is forming stick or elbow. Can you tell me? Can you just tell me which is the case? It is forming stick or elbow. What you will be doing? You will be starting from 20, and you will be going till this newly inserted node, which is 80. So if you go via this path, so it is only one way. I mean, it is tree, so there will always be one path. Okay. So this is a stick, right? This is a stick. Now you want to convert this stick to a mountain. So let me do one thing. Let me erase all the things and let me show you how can I convert this stick to a mountain. It is very interesting. Why it is interesting? Because this is this is actually one of the biggest example that we are doing to convert from stick to a mountain. Okay. Now I will just ask you one thing. If you can do it without my help, then it will be great. Like you can just pause a video and just try without my help. Okay. Convert this whole tree to a balanced tree. What you need to do, just convert this stick to a mountain, and if you want, you can just annotate it before that. So let me say this is X, this is Y, this is Z. So now if you remember, in case of a stick, like Y will come on the top, which means this, and then left of 60 will be lesser than this is 20 and greater than this is 70. Okay, so this is X, this is Z, right? Now you need to insert everything else. Okay, this is interesting. Now just see. Can you insert this 15, this subtree? I mean, like earlier it used to be just one node. Now it is subtree. It is actually not much of difference. So it is actually on the left of 20. So you will say that okay, left of 20, right? Now this thing which is like 85, 80, 80. This is on right of 70. So this subtree which is 85, 80. This is on right of 70. Now this is on left of 70. Okay, 65 is on left of 70. This is 65. What about the remaining nodes? How many nodes are remaining? I think only one is remaining. I mean, one subtree is remaining. This is 65, this is 85. So what is this? This is 50, 50, 30 or whatever, right? So I will do what? I will say that it should be on the left of 60 or left of Y. On left of Y, I go, and then I see, okay, X is already there, right? So I will take the help of X. So I will say that on the right of X it should be there, and also using your common intuition, you can say that okay, this is 50. Okay, just notice only on this 50. This 50 should come on the right of 20 only, right? So it will be 50, and then you will say that then this 30 will be obviously on the left of it, right? So you just need to take care that whether it is 50 or what value is this. Based on that, you just plug in the subtree. So the procedure is exact same whatever we have been doing in case of one node. Now instead of just one node, we have just subtrees here, right? So subtree is also very easy. You just need to focus on these nodes, right? One nodes. Everything else will follow. You just need to focus on these nodes. Like it could be anything. After that, it could be huge trees. Okay, huge trees. It could be anything. You just need to focus on only one node. Okay, one top node of the subtree. I hope you got it. Now this 65 is over, 80 is also over. Now let me insert other nodes, which is 90, 45 and 55. Now to insert 90, I will go right, or I will go on the right, I will go on the right, 90. Okay. Now I don't think there is any imbalance, so things are balanced now, and 90 is over. 40. So 40 go left, go right, go left and go right. Okay. Now let's check whether things are balanced or imbalanced. Now 30 is balanced, 50 is imbalanced. Okay, very nice. I mean, it is very small. So let me not go to the next page. Let me just make a mountain here itself. It is 50, 30, 40. So three nodes, 30, 40, 50. I can make a mountain here only. Okay, 30, 40, 50. So let me make a mountain, and I know that 30 is minimum will be coming here, 40 will be coming here, and 50 will be coming here. Okay, so 40 got inserted. What about 5? 5 is also easy. You just go to left of this and go to the left of this, left of this, left of this. 5 got inserted. And okay, now just find out which is imbalanced node starting from 5. So 5 is balanced, 10 is balanced, 15 is imbalanced, right? So it is also very easy. 5, 10, 15, I need to make a elbow, so I can make a I need to make a mountain. 5, 10, 15. I'm just remembering it. 5, 10, 15. Okay, so 5, 10, 15, right? So 5 will come here, it is minimum, 10 and then 15. Okay, 5 is over, and now 55. So for 55, what you need to do, you go left, go right, and then go right. 55. Now check whether things are balanced. Yes, this is balanced, this is balanced, this is also balanced. 2 minus 1, 1 minus 2 does not matter. So this is balanced. What about 20? 20 is 1, 2, 3, right? 3 here, 1, 2, 1, 2 here. Okay, no problem, it is also balanced. What about 60? 60 will say 1, 2, 3, 4 here, 1, 2, 3. So this is also balanced. So now everything is balanced. So you can say final AVL tree is this, right? This is your final AVL tree, and this is how you can very easily convert any sequence of insertion operation to a AVL tree. Okay. Now let's do one thing. Let me give you some arbitrary example. I mean, instead of giving you some insertion order, let me say that let's suppose this is X, this is Y, this is Z, and these are the subtrees. This could be huge trees, does not matter. Okay, this could be huge tree, just one node does not matter. So these are the subtrees. Can you convert this elbow to a mountain? I think very easy. How? So first convert that to a mountain, and you will say that do you remember where will Y come? I think Y will be coming here. And what about this X? If you do not remember exactly, like you actually do not need to remember, just take some values such that it satisfies this. I think I can take 1, 2, 3. Okay, I mean, do not take 3, 2 or anything like that. It should be a binary system. Let me just take 1, 2, 3 here, and if you convert this 1, 2, 3 to a mountain, then I think 2 comes here, 3 comes here, 1 comes here, and 3 comes here, right? So this is X, Y, Z. So this is Y. So X comes on the left of this, and Z comes on the right of this. Okay. The whole purpose of this exercise to know whether X is coming on the left of Y or on the right of Y. So if you can figure out it easily, then also it is fine. Otherwise, you take some example, you can just figure out where will X come, where will Z come, right? So that is how you can easily do it. Now from here to here it is easy. What about the remaining things? Then also it is easy, like, right? So now in general, let's suppose you have huge trees and you want to just plug these in. Very easy. So just go to Z. So Z is having C and D. So you can say that okay, C and D are as it is. This is C, this is D. What about this A? A is on the left of X, so this is A. What about this B? B is on the right, left of X, left of Y. So on the left of Y it is B, but already X is present, so I will take the help of X. So X is saying that go to the right, right? So to insert this B, go to the right. So which means on the right of this, right? So that is how you can convert an arbitrary imbalanced tree to a balanced tree, right? I hope you got it. So this is one kind of elbow. This is another kind of elbow. So I will just ask you to convert that to a AVL tree. Okay, just do it as an homework. Okay, this is one elbow. Okay, these were the sticks. Okay, I may be interchanging elbow and stick again and again, but these were the sticks. Now convert this elbow to a balanced tree and convert this another kind of elbow to a balanced tree. I will be solving this in the next video, but for now I want you to convert these three things. Like out of these 4 variations, I have converted actually one variation. Now I am just asking you to convert for other 3 variations, 1 to 3 variations. Once you do this, now you know that for any tree, for any arbitrary imbalanced tree, how to convert that to a AVL tree.
So this rotation we have just seen, right? Now let's try to rotate this. First tell me whether it is stick or elbow. Obviously it is stick, right? So this is different stick than this. So it is basically right rotation. Like these are just terms. So this is called right rotation because this is right and then right. Okay. And this is called left rotation. This is again a term because we are going to left and then left. So again this is a stick, right? Now can you convert this stick to a mountain? Yes, very easily we can convert. How? I hope you have tried it, but let me convert it to a mountain. You will say y will be here and x will be I think x will be here and z will be here, right? You can quickly check it whether it is true or false. Like let me take some values. Maybe you can take 1 2 3 and then you can say yes, yes, 1 will be on the left because 1 is the lesser than pi, so that is correct. Okay, anyway, so this is the current configuration. Now can you append this a b c d? Yes, very easily. So z is having a and then b and x is having d. What about this c? C will go to the right of y, but right of y is already occupied, so you will say that c will go to the right of y and I will take the help of x. So x is saying it is left of me, so c will go here, right? And also, like in general, you can take some values and you know that based on the binary search tree property or AVL tree property, where should the c come, right? It should be on the right of y and left of x. So that is how you can rotate this stick to a mountain very easily. Now let's take one more case where this is an elbow and you want to rotate this elbow to a mountain. What you can do, you know that gel will be on the top of this, and then like can you tell me that on left of this whether y will come or this x will come? You can easily say that let's suppose this is 1, this is 2 and this is 3. So if z is 2, then 1 will be on the left, which means y will be on the left and x will be on the right, right? So that is how you can easily figure out whether y will be on the left or x will be on the left. Okay, so and you know how I'm putting these values like 1 2 3 because I know that in order is basically sorted. That's why I'm going with the projection. So if I take the projection, y will come first and then z and then x. So that's why I'm taking the sorted values. Okay, now you know that this a is on the left of y, so very easy to append a. Z, okay, z is currently occupied, so let me append this d. It will be here. So b is saying it should be on the left of z. Left of z is already occupied, so you will ask y. Y will say it is right of me, so b will be here. And okay, this is whole subtree. Okay, I'm not drawing it, but you know that this is a whole subtree. Now what about this c? See, this c will come on the right of z, but right of z is already occupied. So can you tell me where will this c come? I will take the help of x. So x is saying on left of me, so c will come here. Like that, very easily you can convert this elbow to a mountain, right? So this is basically a general configuration where I'm not taking a specific example. Now you know that however big tree it is, you know how to convert that to a mountain, right? However big tree it is. Like here, this a could be huge, right? This a could be huge, this b could be huge, c could be huge. So you know that however big tree it is, for like if you want to rotate, how to rotate, right? Let's see this last case. I hope you have already done, but I'm doing it. So here z will come here, and then you can say that okay, in order, according to the in order, it is sorted. So 1 will be this is 2, this is 3, right? So z means 2, and then 1 will come here, so x will come on the left and then y will come on the right. Now can you tell me where will this ABCD will come? You will say that A will come on the left of X, so it is very easy. D will come on the right of Y, it is also very easy. What about this B and C? B will come on the left of Z, and then I will take the help of X, so B will come here, and then Y will come on the this C will come on the right of Z. So right of Z is already Y, and then I will take the help of Y. Y will say that okay, go to the left of me, so C will come here. Like that, very easily you can basically convert this elbow to a mountain also, right? So now you know that how to rotate a complete AVL tree, however big it is, does not matter to you. Okay. So in case of insertion, we only have one rotation. I mean, one or two rotations, like one or two rotations. So which means like one rotation means I'm converting a stick to a mountain. Two rotations means I'm converting elbow to a mountain. Some people call it two rotation. It does not matter. Like one or two does not matter. If they ask, then they will always say that order of one rotations. Okay. So order of one means it is also covering one rotation, two rotations. So one rotation takes constant time. We just need to manipulate few pointers. So I will show you how. Okay, now let me show you how one rotation is taking constant time only. But before that, one rotation, two rotation does not matter. So before that, let me prove this, where I'm saying that if you are inserting, then you just need one or two rotations. I mean let me just call it one rotation. So whenever I'm saying one rotation, I mean either stick to mountain or elbow to mountain. Okay, so let me show you why we just need one rotation. So let's suppose that this is current case, and you are inserting in this AVL tree somewhere here, right? Somewhere here you are inserting. Now, see, this is an AVL tree, which means this node must be having a balance factor of either -1 or 0 or 1, right? Or +1. So which means that this, if it is having a balance factor of -1, then let me actually draw three cases separately. If it is having balance factor -1, it means that this height minus this height is -1, which means this height must be some, let me call it h -1, then this is h, right? So that the difference is -1. In this case, the balance factor will be -1. And this is one of the case. Another case could be the balance factor is 0, where you are saying the left and right subtree height is actually h and h. And another case could be the balance factor is +1, which means the left subtree height is h, right subtree height is h -1. In this way, the balance factor will be +1. So here it is 0, here it is +1. So there could be three cases. Now you are inserting a node. Okay, maybe you are inserting here or here, does not matter. So let's suppose you are inserting on the left side. So either you can insert here or you can insert here, does not matter at all. Okay, suppose you are inserting here. Now what will happen? Suppose after this insertion, this subtree, okay, this subtree height got disturbed, which means this balance factor of some node here got disturbed. So what you will be doing, you will be rotating here, isn't it? So after rotation, suppose it is getting disturbed, so after rotation, what will be the height of this left subtree? See, rotation will be either like this, from this to this, or from this to this, right? From this to this. So which means whenever we rotate, we are decreasing height by 1. For sure we are decreasing height by 1, right? So whenever we are rotating, for sure we are decreasing height by 1. So if you are inserting here and rotating this tree, so earlier height was h -1, after insertion height got h, but after rotation height will be ultimately h -1 only. Why? Because earlier it is h -1, after inserting it got h. Now if you rotate, like suppose balance factor got disturbed, and if you rotate, then the height will be h -1 only. So with one rotation only, this tree got fixed, which means from this node perspective, nothing has changed. See, before rotation also, this node was having left subtree height, right subtree height is h, left subtree height was h -1 before rotation. Once you insert and then rotate, then again it is h -1 h. So from this node perspective, nothing has changed, isn't it? So just by one rotation, you can fix the things. So similarly, it is true for all the cases. I mean, if you insert here, then height is h +1, but if you rotate, again height is h. So from this node perspective, nothing has changed, right? So just by one rotation, you can fix the tree. So here, in case of insertion, you just need at most one rotation. Okay. So we will see the deletion where one rotation might not be enough. In case of deletion, you may need to keep on rotating till root. Okay. We will see in case of deletion. But for insertion, just one rotation. I mean, one rotation, one or two rotation, whatever you call. I mean, you call this as two rotation, you call this as one rotation. But you got it right. One rotation means that from elbow to mountain or stick to mountain. Okay. So I hope this point is clear. Like if it is not much clear, then take your own time. Like if either you can understand this or you can just skip this completely. It is not required. Just remember that in case of insertion, we just need order of one rotation. Now let me show you how the rotation actually works, which means that how we are just manipulating the pointers and rotating the things. So suppose I want to rotate this stick to a mountain, and I am calling this as LL rotation. Okay, so I want to write a function for LL rotation. I mean some pseudo code or actual code does not matter. I want to write some code for LL rotation. Now can you do it? It is actually very easy. How? Let me first show you without the code. Let me first show you that how it is happening. You know that y will be coming here, and then z will be coming here, and then x will be coming here, and then you know that this AB will be coming like this, this D will be coming like this, and then this C will be coming like this, right? Without the code, you know that how to do things. Now I want to do the similar thing in the code. So can I do it? Let me show you. So let me go to the next page, and here let me do what? Let me basically have something where I'm saying that instead of abstract tree, abstract design of the tree, let me have the pointers in the tree, which means, so instead of saying this x y z, let me have a pointers. So here it is pointing to something, right? And it is also pointing to something. So this is pointed by x, so x is just a little pointer, this is pointed by x, and this is I'm saying this is pointed by y. I mean, does not matter. If you want, you can say it is pointed by y, but in case of the code, we do not actually have y or something. Okay, this x y z are just for our sake of understanding. So let me just explain, don't worry, let me just explain. So here it is pointing to something, it is pointing to something. So it is pointing to, okay, it is pointing to z, it is pointing to z, and then this is pointing to something, this is pointing to something, and this is directly pointing to something which is basically d. Okay, so it is pointing to a, it is pointing to b, it is pointing to d, it is pointing to c. So this is how my current structure look like, right? And I'm converting this to something where I'm saying that this is y, and y is basically pointing to, y is basically pointing to let me go here, z and x, which means this is x, y, z. Okay, y is pointing here, and then this is pointing to a and b, and then this was the x, x is pointing here. Okay, x is already pointing here, and then I want this to point to c and d. Okay, so it is pointing to c and d. This is the complete structure in terms of pointers. So let me just remove this y and z, because I do not have y and z, I just have x. Okay, so I want to convert from this to this. Can you do this? It is actually very easy. How? You can just say, let's suppose your function name is ll rotation, and which is taking x, which means it is taking a pointer to this tree, and you want the final answer is this, and you want to return the pointer to this. Okay, whatever is the pointer to this, you will return this. So can you write the code? I think it is easy. How? You can say that x left should be pointing to c, right? See, this is x, which you are saying. Okay, let me write x y z, x y z. If you are used to of this, let me write a, y, x and z. Okay, so you are saying that let me use different color probably. So let me use a different color. This is x, this is y, this is z, this is y, this is x, this is z. Okay, so you are saying that x left should point to c. So you can say that x left should be pointing to c, means whatever x left right is pointing to, right? You can say something like this, x left right is pointing to, isn't it? Is this okay to everyone or not? See, what I'm saying here is that this x left, this should be pointing to this d is fine. Okay, this x right is fine. I want to have this x left to point to something. So I'm saying this x left should point to whatever x left right is. So x left right is basically this. So whatever x left right is pointing to, that's why I'm equating these two pointers, right? So after this line, can you tell me what will happen to my tree? Let me go to the next page and let me explain you. See, after this line, let me just remove this, and let me just explain you what will happen to my tree after this line only. See, after this line, okay, what will happen? This x is currently pointing to the same thing, and then this will start be pointing to c, this will start pointing to d, and there is something which is also pointing to z and something, and then all, right? So this is pointing to, this is also pointing to c, that is okay. So basically after this line, x is pointing to the similar thing, this left pointer will start pointing to c, isn't it? But there is a problem. What is that problem? Problem is that you cannot modify this x left. If you are modifying this x left, which means if you are deleting this link, then you are deleting the access of this, right? This will be a memory leak. I mean, you cannot access this remaining tree. So if you see, you have the access to this x only. If you are saying x is pointing here, and then left and right are pointing to c and d, then how you will access to this remaining tree, isn't it? So that is why, I mean, I want to do it. That's not a problem. I want to do it, but I want to first basically save this x left something. I mean, let me just save this x left somewhere. Maybe I can say that I will do it. That's not a problem. So my ultimate goal is to reach here, but I will do it after saving this x left to something, which means I will let me just save this into some pointer. So I will say that this x left equal to this is fine. This is completely fine. There is no problem in that. But before I modify this x left, let me save this x left to some t or some y. Maybe you can call it y or t or anything. Okay. So if I'm writing something like this, then it is fine. Which I'm saying that I'm asking our t, which is some little pointer. Okay, it will be a struct node type pointer, a struct AVL node. If you're saying AVL node type pointer, I'm asking this t to point to this remaining tree so that I do not lose the access. Then I can modify this x left. Then it is not a problem, right? So now it is not a problem. Now if I do like this, then I'm not losing to this remaining tree. So I'm saying that t is a pointer which is pointing here and x is currently here. So after these two lines, can you tell me what's the status of the tree after these two lines? So just tell me without watching the video. You can take a pause of the video and just tell me after these two lines what is happening. So let me just delete it. See, after these two lines, I will say that this x will be pointing to the same thing, right? And then it is pointing to D, it is pointing to C. Then there is a different pointer which is T, which is pointing to the remaining tree, isn't it? Which is pointing to the remaining tree. So then the things are fine. Now the things are fine. Now what I want to do next, see, my ultimate goal is to reach here, right? So now currently you can say t is pointing here and this tree is intact. This right is basically let me just say that I want to do this. I want to do something like this. Let me 1 second. Yeah. So current status is this. See, current status is this, that the C is pointed by this y right is also pointing to C and x is also pointing to C. So current status is this, that x is pointing to this kind of a structure, t is pointing to this kind of a structure, isn't it? After these two lines, I will have this. But what I ultimately want, I want this y right to point to whatever x is pointing to, isn't it? So very easy. So I can say this t right should point to whatever x is pointing to. So these are just 3 lines I need to modify this whole thing. If I do that, then I will say that this t right, which means this thing, should be pointing to whatever x is pointing to, right? And then I want to return this pointer to the root of this, which means I want to return this t. So I can say return t, so that whoever is calling this rotation should be basically pointing to this root node, right? So I hope you got the little bit of picture. So how we are modifying the pointers. It is just a normal pointer manipulation, right? So let me just show you what is happening here. Okay, 1 second. Let me remove this. So let me just show you what is happening here. I am saying that let me store this in the T, and then x left. I am saying that x left should be pointing to whatever x left right is pointing to, or maybe you can say t right. Okay, so because x left and t both are actually same. After this line, x left and t both are same, so you can say t right, and then t right should be x, right? So you can say t right and then t right should be x, and then you can return t. So this is the final code. I hope you are getting. You should be actually able to write this code. This is not a tough code. It is a very easy code, right? So once you understand pointers and struct and all and linked list and all, then you should be very comfortable by writing this rotation code. Now, is this all, or do I need something else? There is one thing that I need, which is basically updating the height. So I should also be updating the heights of the nodes. Why? See, this is an AVL tree, and AVL tree struct node look like this. This is not a general tree. So struct node of AVL tree, or you can say AVL node or whatever, right? It looked like this. It has the pointers, left pointer, it has the right pointer, it has data, it has something else also. What is that? It has height, right? Height of that node. So you can say these are the pointers, and this is integer, this is also integer, right? So this is the structure of, or definition of, this AVL tree node. Now given this, you have basically converted that to the mountain. That is okay. So let me just show you the how the mountain is looking like. So mountain is looking like this. Here it is actually Z, it is A, B, this is x, this is d, this is c, and y or t is pointing to this. Okay, this is the current status, and x is pointing to this. X is pointing to, you can say, this. Now after these 2-3 lines, this is the current status. Now what you want, you also want to update the height. So to update the height, you can say that x height, you first need to update the x height. You can say it is very easy. How? You can just take the maximum of x left height, which is actually c height, comma x right height, right, plus 1. You can take the maximum of x left height, x right height plus 1. So that is how you are updating like these are basically 4 values. One is left pointer, right pointer, data, and height. That is how you are updating x height. Now to update this t height, you can do the same thing, which means you can write here that t height. One second. You can write here t height is equal to max of t left height, let me just write L. Okay, L means left, actually left height, comma t of right height plus 1. Okay, that is how you can do it, and then you can just return t. So basically these are just 2-3 lines of code to manipulate the pointers, and then you can update this x height and t height. Now remember that you cannot interchange these 2 lines. Why? Because if you are updating t height first, then x height, it is actually making use of x height. T left is z, and t right is x, and x height is not updated yet. So that's why it will wrongly update the height. So first update the x height and then only update the t height. Do not interchange these 2. Okay, you cannot interchange. Once you update this x height, then only you update this t height. That is all. I hope you got it, right? So this is how we can rotate the things. Now let me show you how to rotate in case of elbow. Okay, this was the rotation in case of stick. Now I want to rotate an elbow. It is also very easy. In fact, it is extremely easy if you already have functions to rotate for sticks. So basically what does happen, like in case of this elbow, in case of this stick, let me say that this is an stick. Now what you are doing, you are rotating at x. So you are saying that I'm performing rotation at this node. Okay, it is called like rotation at x. Now in case of elbow, you want to perform rotation at x, right? But it will happen in 2 steps. First I will perform rotation at y, which means I will consider this, okay, let me call it p or something. So I will consider this whole thing as an stick. I will convert that to a mountain. So I will perform this right rotation. See, I have just shown you the code for left rotation. Similarly, you can write the code for right rotation, right? So once you write the left and right, then you can make use of those codes here. How? So let's suppose you have the code for right rotation. Then what you will be doing? You will be first converting this stick to a mountain on y. Okay. So what you will be doing? You will be saying right rotation at y. Okay, so here you will be saying right rotation at y. Once you do that, then it will be converted to a mountain. Then convert this this complete thing at by saying the left rotation. So on x. So you will be saying left rotation on x. How? Let me just show you step by step. See, this is the current status you have. Now can you convert that? Can you convert this stick to a mountain? I think very easily. This x is as it is. This d is as it is. Now can you convert this? So this z will be coming here, y will be coming here, this, let me call it p or something. So p will be coming here, this y will be coming here, and then this p is having this p is basically like, I mean, this is the complete subtree, which is c, and this y is having a, and then this b is basically left of z, so b will be coming here. Like that you can very easily convert this stick to a mountain. Now whatever you're returning, so basically this stick to a mountain you can convert, which means x left. So you will say this right rotation will return the pointer to z, right? See, earlier this left rotation is returning the pointer to this top node, right? So I'm returning t, which means I'm returning pointer to the top node. So whenever you're performing this rotation, so I will be returning pointer to the top node, which is z. So I will say that x left should be pointing to whatever this right rotation is returning, because right rotation will return the pointer to z. So x left will start pointing to z, isn't it? And then I will say that, okay, after this line only, after this one line only, I do have this structure. Then I will say that I now want to convert this stick to a mountain, which means then I will say that okay, perform the left rotation on which node? On X. This time on the X, right? Now perform this left rotation on the X, and then I will return whatever whatever this is returning, right? Because I want to return the pointer to the top, so it will return actually the pointer to this Z. So I will return the same thing. So let me show you the code. So see here, like first I am passing this X left because I want to perform the rotation on this Y. So I am passing this X left on this RR rotation, and then whatever it is returning, I am storing this into the X left only, and then I am performing the rotation on the X. So after this, basically I will be having some X and then I think Z or something like this, right? So it is this Z Y and like this Z Y and like this, and then I want to perform rotation on X. So basically I can say that I want to perform left rotation on the X, and whatever it is returning, let me just store this in the X temporarily. I am storing that in the X. So whatever it is returning, I am returning the same thing, right? I'm returning the same thing because whoever is calling this should be having the top pointer. So I mean you can store this in the some temporary variable, maybe T, okay, T, and then you can return T if you want to. That's not a problem because anyway X is a local variable to this function. So I'm just modifying X, does not matter actually. You can take T if you want, struct node T, struct node start T, right? You can do like this. I hope you got it. So now what you can do as an exercise, I have shown you two codes. I have shown you how to convert this left rotation to a mountain using the code. I have also shown you this, which is left right or elbow, this left right to a mountain. Now these two are done, right? Now what two are left? Only two things are left, which means this right to a mountain. This you can do as an exercise, and then this, if you want you can do it, otherwise there is no problem. And then this this kind of elbow to a mountain. So basically this you can take as an exercise, okay? Now you can comment your code, or you can write it on pen and paper. You can comment in the video below. So basically in the GATE exam, they will not ask you to write the code or anything. This is just to make you understand the things very deeply. We have covered AVL insertion in very much depth, okay? And also we will be covering AVL deletion in very much depth. So every topic we are covering in depth. It does not mean that in the GATE exam they will ask you to write the code. No, they will just ask you to analyze these things, right? They will just ask you to analyze, like, what does this mean, what does that mean, okay? They will not ask you to write the codes. But I'm just explaining in such a way that even any kind of question that comes in the GATE exam, you should be able to solve that question, because now you know the deep understanding. Actually this is extremely easy. Maybe I do not know if I have made it complicated, but it is extremely easy. You just need to manipulate few pointers here and there. That is all you want to do, okay? So now like we are done with the insertion. You can do one question which which I have taken from University of California. So you can do one question which is based on the insertion. It is just for your sake of practice, and I do have the answer in the next slide. So you can see the answer step by step also. Okay, so this is the final answer you should be getting. This is the question related to the insertion. If you want, you can try this question and see the answer later. So now we have seen AVL search and AVL insert. It is a right time to see AVL delete. AVL delete sometimes becomes a bit tricky, but in this video I will try to explain this topic in very lucid way. So let's start with AVL deletion. Suppose that these are the sequence of operations that I want to perform, which means first I want to insert 6, then 3, then 7, then 1, and then 7. Then I want to delete 7. So inserting 6 is, I think, very straightforward, and then 3, and then 7, and then it is balanced, then 1. So 1 will come at here, and again it is balanced, right? And then delete 7. So I want to delete the 7 now, right? So I hope you got it, like how we are inserting. Now I want to delete 7. So this is the first example where I'm going to delete. So how I'm going to delete is very simple. First step is to delete just like binary search tree. So since this is a leaf node, this 7 is a leaf node, so I can easily delete just like a binary search tree delete, right? So it is just like a BST delete plus balancing, right? So if you remember from our AVL insertion, it was BST insertion plus balancing. Similarly, AVL delete is also BST delete plus balancing. So BST delete is very straightforward, but balancing becomes little tricky in this case. So let's just see. So BST delete means you are just going to delete the 7, and then now you are having this kind of structure, right? So 7 is now deleted. Now you want to balance it. Since it is unbalanced, see 7 got deleted here from here, and now the 6 becomes unbalanced, right? So now you want to balance it. Now it is very easy to balance in this case since it is just a stick. So how you can balance it? You can just say that you can convert this stick to a mountain very easily. How? You can say that this is 3 in between, in middle you will be having 3 and then 1 and then 6. That is how you can delete the 7. So these are the sequence of operations that you can perform very easily, right? Now let's go to some other example. So now this is, consider this as a completely new example, and here I am not having some node numbers. If you want, let me just have, so it is like, let me just have in the in order sequence so that I can easily fill out the numbers. Let me fill 1 here, 2 here, 3 here, 4 here, 5 here, 6 here, 7 here, right? So which means 1 will be here, 2 will be here, 3 will be here, 4 will be here, 5 is here, 6 is here, and 7 is here, and it's a valid binary search tree. It is also AVL tree because no node is getting imbalanced, right? So that's why it is also an AVL tree. Okay, now let's say that I want to delete this one. So how can I delete this one? Since it is a BST delete first of all, then I can delete it very straightforwardly, right? So I can delete this one. But after deletion, I also have to balance. To balance the things, I will go from this deleted node till the root. Okay, so remember this, like in case of insertion also I was doing the same thing, from inserting node to the root. Similarly from this deletion node to the root. So if I go to the root, I will encounter this 2. I will say that this 2 is balanced because this is now a leaf node, so there is not a problem. 2 is balanced, right? Now I will do what? I will keep on going to this 3. I will not stop at this 2. I will keep on going to this 3. So now I will go to this 3. I see, okay, 3 is unbalanced. Why? Because this height is 1, 2, 3, and this height is just 1, right? So it is 1 minus 3, which is minus 2. That's why the balance factor is minus 2. That's why this 3 is unbalanced. Since 3 is unbalanced, I will do what? I will do balancing. Now, to do balancing, I first have to figure out whether this 3 is forming a stick and elbow. Okay. Once I figure out whether it is forming a stick or elbow, then the things are very easy. So now tell me, it is forming a stick or an elbow, which means should I be going like this? Okay, see this here there is no scope of stick and elbow. I will actually tell you the proper method, but for now I'm just working with some intuition. Okay, so now you have two options. Okay, either you can say that this is a stick, which means you can say that it is forming a stick like this, or maybe you can say that this is not a stick, this is an elbow. So how it is forming an elbow? You can say that this is an elbow, right? So like this, you can say this is an elbow. So either it is a stick or an elbow. Which option I should go for? Just think about it. Okay, so here let me tell you the rule. What you are going to do, you are going to this 3 which is unbalanced. Now you will go to its child, which is 5, right? Now at the 5 you have two options to go. See, from 3 to 5 there is only one option. Now from 5 either you can go to 4, which will make an elbow, or you can go to 6, which will make an stick, right? So what option you are going to choose depends on the child of 5. So 5 had 2 child. Now measure the height of this left subtree, which is actually 0, right? Height of this left subtree, because left subtree is having just one node. So height of this left subtree is 0. Height of the right subtree, which is this, is actually 1. So whoever is having higher height, I will go for that, which means that I will go for this this stick. You're getting? So let me tell you what I'm doing. I'm at this node, which is first imbalanced node. Okay. Now I'm going to tell you the proper algorithm or proper step-by-step procedure. This is the first imbalanced node. I will go to one of its child, the child who is having the higher height. Okay. So I will always go to the child which is having the higher height to determine whether it is elbow or stick. This step is very crucial. Let me just tell you that you will struggle to understand this topic if you're not paying attention here. Okay, if you try to understand this from other online sources, you will get very much difficulty. Like this is I'm telling based on my experience. Okay, so what you are going to do, you are at this imbalance node. Then you are going to choose a node which is having the higher height. Okay. You go to this 3, it is the first imbalance node. Now 3 has 2 children, which is 2 and 5. You go to a children which is having the higher height. Obviously, after deletion, 2 is just a leaf node. It will never have a higher height actually. Okay, I mean, I am deleting from this branch, right? So this branch will never have the higher height. So I can very safely choose 5. But for the algorithm point of view, let me tell you very step by step everything. So I will compare between 2 and 5. Whoever is having higher height, I will go for that. Tell me between 2 and 5, who is having higher height? See, this 5 is having height of 2. 2 is having just height of 0. Obviously, 5 is having the higher height, right? I hope you are getting. So what I'm saying here is that like this is my tree, and after deletion it becomes like this, right? So let me do one thing. Let me just fade this away. So let's suppose this 1 is deleted. Okay, 1 does not exist here anymore, and let me delete. Let me just remove every other unnecessary things, and let me explain this very properly. Because once you understand this, the deletion will become very easy. And this is the only concept we need in the deletion. We do not need anything else. We just need to understand that how to identify between elbow or stick. Once you identify between elbow or stick, then you can easily rotate. I know now you are expert of rotation, so you can easily rotate once you identify elbow or stick. Okay, so this is my current tree that I have. Now you go to first imbalance node. What is this first imbalance node? This is 3. Now you go to this 3. At this 3 you will say that okay, go to its left and right, see whoever is having higher height. So this is having height of 0, this is having height of 2. That's why I will say that to identify between stick and elbow, I will choose this path. Okay. Now I am again at 5. I will go to the node whoever is having higher height. Who is having higher height? 6 or 4? Obviously 6. 6 is having height of 1. 4 is having height of 0. That's why I will say that this is an stick. This is an stick. I hope you got it. Now you just rotate it. Once you identify this is an stick, see this step is only crucial. Once you identify this is an stick, you can rotate it. So let me just write it here. You go to first imbalance node. Okay, first imbalance node, and then choose between higher height. Choose between higher height. No. Okay, choose a node, choose a higher height node basically. Okay, choose a higher height node or child. You can say child. I hope you got it right. Now just follow this recursively, which means iteratively recursively, which means you go here, then again just go to the node whoever is having the higher height. Suppose this is having higher height, then it will be elbow or stick. It will be elbow if this is having higher height. Now suppose if this is having higher height, then it will be elbow or stick. Then in this case it will be stick, right? So now you go to this 5 and the 6 is having higher height. That's why it is a stick. Now just rotate it. Let me just annotate it so that like it becomes little easy. So in case of a stick, if you remember that 5 or y will come on the top, and then lesser than 5 is 3, and then greater than 5 is 6, right? Now you can append every other node. So 3 left is 2, 3 left is 2, and then this 5 left, okay, I will append it later. 6 right is 7, and 5 left is 4. So I will go to 3. I will ask 3. It will say that it is greater than me. So that's why it should be on the right of this, right? So that is how you can make it balanced. See, this was imbalance. It is balanced, right? I hope you got it. So let me quickly explain you what I did from starting, right? They asked me to delete this one. Let me just write here, delete 1. Okay. They asked me to delete this one. I did what? I did first, delete using the BST deletion, which is very much simple. And then I am going from the deleted node to the root. Then I found out that okay, 3 is first imbalance node, and then from 3, it is my responsibility now to determine that whether it is forming stick or elbow. So to determine whether it is stick or elbow, what you need to do, you just go to its child, which is 2 and 5, and then compare who is having the higher height. 5 is having higher height. Now from 5, go to 4 or 6, depends on that who is having the higher height. So here 6 is having the higher height. Okay. Now you got this balanced tree, right, after rotation. Now tell me, will I go wrong if I choose between this stick or this elbow? So I followed the step and I have chosen the stick, right? Suppose what if I choose elbow, which means that instead of a stick I say, like by mistake, suppose I choose this elbow, I say that it is not a stick, it is an elbow. Then let's just see what is going to happen. Okay, so let me just write here that by mistake I am choosing, okay, it's not like intentional, maybe by mistake I am choosing this is an elbow. Okay, what if what if, let me write in bracket, by mistake I choose elbow, what's going to happen? Let's just see this. Okay, so in this case, let me annotate it. This is x, this is y, and z is now this, right? So you can annotate it if you want. I mean, sometimes it is easy. So you can say z is on the top in case of this elbow. So you can say this 4, which is z, is on the top, and then 4 lesser is 3, which is x, and then 4 greater is 5, which is y. Okay, now let's just append other nodes, which is 6 7. This 5 right is 6 7. It is very easy to append. You can say it is 6 7, right? And then you will say that okay, this 2 is remaining only, right? So this 2 will come on the left of 3. So left of 3, this 2 will come. Now tell me, is this balanced? See, you are choosing elbow, which is by mistake, that is okay. But now tell me, is this balanced? Clearly no. Why? Because see this, is this balanced? No, this is again a stick. So that's why it is wrong. Okay. So it is a complete mess up if you choose a wrong selection, which means instead of a stick, if you choose elbow, instead of elbow you choose a stick. So I think the algorithm is extremely simple. You just need to understand it. I made it so simple to understand that you should be following it. Okay, to be very honest. So now you know that how to delete. Now let's just do more practice. Okay, I will tell you more variations, more practice, but the core concept is same. Now look at the slide again. The core concept will remain same, which means from the deleted node I will go to the root, till the root, and I will find the first imbalance node. Okay, and then from there I need to choose whether it is a stick or elbow. I will follow this procedure. I will choose a higher height child. That is all. Let me do more examples. Suppose so I think this example and this example are different. Okay, so earlier this node was not there, right? So earlier, yeah, there was no node like this. Okay, so now let's do this example. Suppose again, okay, for your sake of convenience, let me just fill these numbers. Maybe it is 1, it is 2, it is 3, and then it is 4, 5, 6. I hope that you know that how I'm filling the number. I'm basically projecting it, and then I'm saying that okay, let me fill in the sorted way, and in this way I will never go wrong, right? Okay, now suppose these are the numbers, and suppose they are asking me to delete again this one. Okay, so let's now delete this one. Now you will say that 2 is balanced. Now go from deleted node to the root. 2 is balanced. Now go to this 3. 3 is unbalanced. Why? Because this height is 3, and suddenly the left height has become 1. So that is why this 3 is imbalanced, right? So now I need to do what? I need to basically select whether it is a stick or elbow. So I will go to 2 and 6. I will say that okay, this is very easy selection because 6 is having higher height. Then to choose between 5 and 7, I will say that whichever is having higher height. So tell me which is having higher height. Now height is same, right? 5 is having height of 1, 7 is also having height of 1. Now this point is again crucial, okay? Which says that in case of similar heights, you always go for a stick, okay? Which means I will go for a stick like this. So if I go for a stick, then let me just show you what's going to happen. If I just rotate it, you will say that this is x, this is y, this is z, right? And y will come on the top, which means like this, and then 6 lesser is 3 and 6 greater is 7. This is x, this is z, and you can just append these things, which is 2, I think, and this is what else is remaining, 5 left, right? Okay, this 6 left, which is 5 4. 6 left is 5 4. Let me append it later. 7 right is 8. Okay, 6 left is remaining only, which is this subtree 5 4. So 6 left means I will go here. I will say that okay, 6 left is already present. Then I will take the help of this x. X will say that okay, it should come on the right of me because it is greater than me. So it is 5, and this is not like 4. Okay, this is the left child. Okay, so you will see that it's 4. And now things are fixed. You can just check that this tree is balanced, right? Now let's see a case. What if by mistake? See here I am getting a tie, right? See, if I'm at 6, I'm getting a tie because 5 is having the similar height then just like a 7. So what if by mistake? So the rule is that I will always go for a stick in case of similar height, right? But what if by mistake I choose an elbow? Suppose I do this. Now suppose that this is x, this is y, this is z. Suppose by mistake I go like this. Then let's just see what's going to happen. This is 5, right? This z will come here, and then lesser than this is x, and greater than this is y, right? And then what you are going to do? You are going to just append these things. 7 8, that is okay. 3 2, that is okay. And I think this 5 4 is remaining. Okay. This 4 is remaining. That is on the left of this, right of this. Okay. Now tell me, is this balanced? Obviously no. Why? Because see here, what is happening, right? This is not balanced. So in case of similar height, always go for a step. Okay. So here, let me write the rules. What we have seen, let me just write algorithm step by step. Step 1, BST delete, right? BST delete. Step 2, balancing, right? Now inside balancing, I will go till root and find first imbalance node, right? And now from here, identify stick for elbow. Now this is bit tricky. So from here to choose this, like I will go for higher height, higher height child. If, okay, let me write it here only. If, so it is actually a point under this this only. So let me do one thing. Let me just shift it so that I can write it here only. 1 second. So I will say that if, so let me just write it here only. So I will say that if heights are same, then go for stick. Okay. So basically, some people think that going for stick is actually convenient way. Like you can go for elbow also. No. So let me just write that also. So in case of similar height, okay, in case of similar height or equal height, going for elbow is wrong. Basically, I mean, I'm not going for stick just for the sake of convenience. It is the only way. Okay, we are not going for stick. We are not going for stick just for sake of convenience. For sake of okay, going for elbow is actually wrong. Going for okay, I hope that is clear to everyone. That we are not just saying that okay, for the convenience you go for the stick. No, if you go for the elbow, it is wrong. Okay, by mistake, if you go for elbow, going for elbow in case of equal height, right? So I hope the deletion is now completely clear. So these are the steps only. So very simple, right? BST delete, and then I will go to the root to find the imbalance node. Then I will choose the node which is having the higher height. If the height is same, then I will choose the stick instead of elbow. That's all. So see here, like this is actually not necessary, but I'm just telling you. This is, let's suppose, the first imbalance node or unbalanced node. Then I will choose between this y and this another child. Okay, I have not circled it down, but that's okay. Okay, so I will choose between this y and this node for the x, and I will say that okay, suppose that y is having the higher height. So it is saying the child of x with the larger height. Suppose this is y. Then I will again choose between z and this circled node. Okay, this circled node, whoever is having higher height. Suppose that this node, which is child of y, is having larger height. Then this is a stick. Okay, then this is a stick. Right? So I'm always following the larger height nodes. Okay, larger height nodes. So for the x, I will follow between this x. Let's suppose this is p and this is q. So between this y and p. Okay, between this y and p, I will choose p y. Why? Because this is having the larger height. Similarly, between this q and z, which are both the children of y, I will choose z. Why? Because z is having the larger height. That is one. Okay. So I will always choose the larger height. So similarly, if I am going for elbow, then the region must be that it is the unbalanced node, and then x is having the like this y is having the larger height between this node and this y, and then similarly this z is having the larger height between this node and then this z. Okay, and then that's why it is forming an elbow. Okay, so I will always follow the larger height node or larger height child. I hope that is fine. So now see this. like this is the third case when the heights are same. Suppose this node height and z height is same. Suppose this node height and height is same, and I'm going for the elbow, okay, which is actually wrong. So going for a elbow, which is not a correct way to do it. So what I will do, I will rotate. Okay, actually I know how to rotate directly. I mean, since I have taken this image from the internet, and they actually rotate in 2 steps, but that's okay. I mean, I know how to rotate in just 1 step. So they are rotating in 2 steps. You can just completely ignore this middle step. That's not a problem. Okay, so I got this right. Now if I get this again, then there are the high chances that again this tree is imbalanced. Okay, again this by may be imbalanced. Okay, so let's not go for these images. I hope you have understood from the example that if you are going for the elbow, then the going for the elbow may be wrong, because this by may be again imbalanced, right? See, this by is imbalanced. I hope you got it. Okay? That's very easy. Now you know the algorithm and you know everything. Now there is one more thing that I want to tell in case of deletion, and then we will just do the practice. So the last thing that I want to tell in the deletion is this, that if you want to delete something, let's suppose, okay, let me first fill these numbers if you want. Let me fill these numbers with, this is suppose 1, this is 2, and then this will be 3, this will be 4, this will be 5, then yeah, I think this will be 6, this will be 7, this will be 8, this will be 9, this will be 10, this is 11, right, and this is 12. Yeah, so yeah, I think this is a binary search tree, regular tree. Okay, now suppose they are asking me to delete this one, they're asking me to delete one. Now this case is little interesting. I mean, the elbow, identifying elbow or stick, these cases are over. There is just one more thing that I want to tell you. Okay, so if you delete this one, then check for the imbalance node. Which is first imbalance node? This 2 is not imbalanced, 3 is not imbalanced, okay, and 5 is imbalanced. So basically in this case the root itself is imbalanced. So basically sometimes what may happen, that suppose that 3 is also imbalanced. Okay, I mean, I will tell you the case in the next video, where suppose the 3 is also imbalanced. Okay, I do not have that particular example currently, but suppose the 3 also imbalanced, and you are fixing this 3. Once you fix this 3, it is not necessary that root will also get fixed. So basically in case of deletion, I will tell you the example, don't worry. In case of deletion, I may have to keep on fixing till the root, which means that once I fix this 3, I may still have to fix this 5. I will tell you the example. So basically in case of insertion, only one rotation is enough, but in case of deletion, you may have to keep on going till the root. So basically log n rotation might be required in case of deletion. I will tell you this example in the next class. So here currently I am just telling you one idea, that in case of deletion, you may have to keep on fixing till the root. Okay, so number of rotations will be order of log n in case of deletion. In case of insertion, once you fix this only, the things are fixed. Okay, so I will tell you this example in the next video. So there are two major points in case of AVL deletion. One is that identifying stick and elbow. Second is that once you fix one rotation, okay, once you fix one node, then you cannot stop there. You have to keep on going till root. Now let me take some examples and let me basically exercise these 2 points on those examples. Let's take this question. So this question is saying delete 1 from below 3 AVL trees, which means 3 like actually this is these are 3 AVL trees, different AVL trees with the small variations. Okay, so all of these AVL trees are independent. Do not think that they are having any dependency. So let me delete one from this AVL tree, then this AVL tree, then this AVL tree. So what I did, I have actually separated it out. So this is A, okay, and this is B, and then this is C. So there are 3 A, B, C I have written in the different slides. Now let me delete one here. If you delete one from here, what you are going to get? You are going to say that okay, this 2 is balanced, then this 3 will be imbalanced. Why? Because this height is 1, 2, 3, but this height is just 1. So since this is imbalanced, I will find whether it is an stick or elbow. So you will go to 5 because 5 is having higher height. From 3 you will go to 5. Then you will go where? You will just say that okay, from this 5, 4 is having a lesser height and 6 is having the higher height. So you will go to the 6, right? This is how you can say that this is a stick, isn't it? Now, once you identify that this is a stick, you can easily convert that to, like you can easily rotate it, right? So let me do it right away. So let me do one thing. Let me just minimize this, or just have the lesser size of this, and then let me rotate it. Okay. So here you can say that 8 is as it is, and 8 right tree is also as it is, which is actually having 1 2 3 4 height. Okay. So this, this is having 1 2 3 height, and including this 8 is having actually 4 height, right? From the left side. So let me just write 3. This tree is having 3 height. Okay, and it will be as it is actually. Okay, that's why I'm not making it again and again. Now here it will be, middle will be 5, right? Middle will be 5, and then this will be 3, this will be 6, right? And this is 3 height. Okay, and then you will say that okay, this 2 it will be coming on the left of 3, right? And then this 4 will be coming on the left of 5. Okay, I will do it later. So 7 is coming here, and then 4 will be coming on the left of 5, so which means right of 4, right of 3, right? This is how you can basically rotate this stick to a mountain very easily. Now, is this done? Like, have I deleted one, or like there is something else that I need to do? Just think about it. Should I just go to the next question without even looking at anything else? No. Why? Because you cannot just stop at one fix. You have to keep on going. Now go to 8. Check whether this is imbalanced or balanced. Okay. So this height is 2. This height is 3. So yes, 3 minus 2, it is balanced. Fortunately, it is balanced, but it does not mean that after one rotation you will stop. I will give you the example. Don't worry. But here it is okay that you are saying that okay, you are going to stop. Fortunately, it is balanced, but it may not happen all the time. Okay. So you got it right. So from this here I have identified that this is a stick. Now let me say that by mistake, okay, by mistake, not intentionally, by mistake I say that this is not an stick, this is actually an elbow. Suppose by mistake I say something like this, that this is an elbow, okay, which means I say that okay, from this 3 to 5 to 4, okay, then will this work? This should not work, right? You should not keep on trying it like this again and again. I will just show you 1 or 2 examples that if you make some wrong choice, it will not work. So if you just rotate it, it will be like 4 will be on the top, and then 3, then this will be 5, and then this will be 6, this will be 7. See here, this 5 is imbalanced, right? This 5 is imbalanced. So that is why if you are taking by mistake, if you are taking elbow, then this y, this is x, this is y, this is z, this y might be imbalanced taking elbow. So taking elbow might be wrong, right? Because this y is imbalanced. So you go for the stick. Why? Because this was having the higher height. 6 was having the higher height, right? I hope that is fine to everyone. Now let's do example B. Okay, so there are I think 3 cases, A, B and C. So now let me do B. So in case of B also they are saying delete 1. So they are saying that delete this 1. Let me just delete it. 2 is balanced, 3 is imbalanced, right? Because this height is 3, this height is 1, so 3 is imbalanced. Now let's just identify whether it is an stick or elbow. Just identify it. You go to 2 and 5, obviously 5 is having higher height. Go to 4 and 6, who is having higher height? Just very easy to answer, right? So 4 is having the higher height. That is why it is an elbow. Okay, this is not a stick. Why? Because 4 is having the higher height in this case. So that's why this is an elbow. Can you convert this? Yes, it is easy. How? You can just basically use this elbow to mountain thing, and then you can very easily convert this elbow to mountain. So let me just try it. Let me just say that okay, from here you will be getting, this is 4, this z will come on the top, this is 3, this is 5, and then this is 8, and this right sub tree is I think having the height of 1 2 3, right? So this is having height of 3, height is 3, right? And then you have 2 which is on left of 3, that is okay. You have 3.5 which is on left of 4, okay, I will do it later. On right of 5 you have 6, on left of 4 you have 3.5 which is actually right of 3, okay. That is how you can rotate this this elbow to a stick, right? This elbow to a mountain. Now just check whether okay, before I do that, tell me, am I done? After just one rotation, in case of deletion, am I done? See, if it could have been insertion after one rotation, you are always done. You do not need to check again and again. But in case of deletion, you just fix this, right? You just fix this. But are you done? No. You have to check for 8. So just check for 8. This height is 2. This height is 3. So yes, 2 minus 3 is minus 1. So 8 is, fortunately 8 is balanced. But it may so happen 8 is imbalanced. Okay. So I cannot just write away stop. I hope you got it, right? So this B is also very easy to convert to a balanced tree after deletion of 1. Now let me show you by mistake. By mistake, if you choose maybe like instead of this elbow, if you choose stick, okay, by mistake. I mean, I should not be doing it again and again. I think I'm just wasting time. But maybe for the sake of explanation, let me do it for one or two examples. By mistake, if you choose this stick, okay, then what's going to happen? Just see here. See, if you are going to convert this, you are going to get what? You will say that 5 will be on the top, it will be 3, it will be 6, and then on the okay, let me append all the notes. So it will be 2, right? It will be 2, and then this is 6. Okay, yeah, things are fine. So now here on the left of 5, it will be 4 and 3.5, which means 4 and 3.5. Now see here, this is basically, is this balanced? No. Why? Because this height is 1, this height is 1, 2, 3, right? This 5 is again imbalanced, right? So what's the point of taking this as an stick? There is no logic, right? So whenever you are having the higher height, then go for that. But in case if you are having the similar height, then go for the stick. Okay, so see, there are the 3 examples that I have talked about, right? So this is the first example. Here I think after deletion of 1, I have went for the stick, and here after deletion of 1, I have went for the elbow. So here after deletion, I have went for the stick because of the higher height of 6, right? And after deletion of this one, I have went for this elbow because of the higher height of this 4. So here I'm going for the elbow. So what is the reason for the stick? Because of higher height. What is the reason for the elbow? Because of the higher height. Now let's see this third example, which is C. Okay, so let's do this third example, which is saying that this is C, the delete 1. So they are saying delete this one. Now in this case, if you do that, then you will say that okay, 2 is balanced, 3 is imbalanced clearly because it is 1, 2, 3, that is why it is imbalanced. Now you identify whether it is stick or elbow. Tell me, okay, just take your time and tell me whether it is stick or elbow. See, you will go to 5 for sure because 2 is having lesser height than 5, definitely. Now you are stuck, like 4 and 6 both are having the same height. Now from this 3, where to go? Like from this 3 you are going to 5, and then from this 5 where to go? I should go to this 4 or I should go to the 6? I think I should go to the 6. Why? Because in case of similar height, I will choose a stick. That is why I will go to the 6, right? So that's how I can convert this to my desired thing, which means I can actually rotate it. So let me quickly rotate it and let me show you what is the final result that we are getting after deletion of 1. Okay, so let's just do this quickly. Now you will say that this is a stick, so 5 will come on the top, this is 3, this is 6, and then this is 2. Then on the 5 you will say that okay, this 7 will come here, and the 5, this 4 subtree on the left of 5, which means here, right? Okay, and then on top of that 8 and some subtree is there, which is having height 3, right? 3 height is there. Now tell me, this 5 is balanced. Obviously it has to be balanced because I just rotated it. Now check. Okay, before I actually do it, tell me, should I stop here? Am I done with my deletion? No. Why? Because just one rotation does not make sure that the whole tree is balanced. Maybe the ancestors are not balanced, right? So basically you have to go till the root. Now check this 8 is balanced or not. So in this case, I think this is 3, 1, 2, 3. Yeah, this height is also 3. So in this case, this 8 is also balanced. Fortunately, this 8 is balanced. That is why I do not need to worry about anything, right? Maybe sometimes 8 is imbalanced, right? So there are 3 cases that I have shown you, right? So in the first case, you are going for the stick. Second case, you are going for the elbow. Third case, again you are going for the stick, right? So a third case, you are again going for the stick in case of deletion of 1, right? So here you are going for the stick. Here you are going for the elbow, right? In case of deletion of 1. So what are the reason for these 3 cases? First case, you are going for the stick because 6 is having the 6 is having the higher height than 4, and in the second case, higher height. So this is higher height case because of the higher height. This is also because of the higher height, right? This is because these are equal height, right? 4 and 6 are having equal height, but we will go for a stick, right? In case of equal height, we are going for a stick. I hope you got it. So this is the third example, right? Now let me do one thing. What if I by mistake in the third example, by mistake if I basically choose for the elbow? Let's just see what's going to happen. Okay, this is the last example that I'm showing you like that, the by mistake. If I'm doing this, if I'm doing that, like I should not be doing it again and again, but for the last example I'm doing it. Okay, so suppose by mistake you do this, right? Then you will say that 4 will come on the top, and then 3, then 5, right? And then again you will say that 6, 7 will come like this, which is clearly saying that this is not a balanced tree, right? See, this 3.5 will come on the left of this, which means here. Okay, so you will convert that to this tree, and then 8 and these things are there obviously, but you will say that this is not a balanced tree, right? So that is why going for the elbow by mistake, elbow is wrong, right? By mistake, if I'm going for elbow is wrong, going for elbow is wrong. So I hope these three things are clear to everyone, right? So in these three examples, I have tried to convey the three things, which means like in case of equal height, go for the stick. In case if it is not equal height, go for the higher height. Now it is up to the question whether it is a higher height is leading you to stick, or higher height is leading you to elbow. Okay, I hope you got these three examples. Now let's solve these two examples. Here I want to convey one other thing. So basically these are the two things that I wanted to convey to you. One is that one second. Yeah, one is that identifying stick or elbow. Okay, so I have shown you ABC three examples. In one example I am taking stick, elbow, and then stick. Why? Because here, because of the higher height, here because of the higher height, here the heights are equal, then I'm going for the stick. So identifying stick or elbow, like I have given you three examples just for this single point. Now the second point is also important, which says don't stop, just keep on going till the root. Okay, so let me give you another example where I will emphasize this second point. Okay, so it is just like that I'm emphasizing these two different points using two set of different examples. Okay, I hope you are getting. Now let's solve this question. This question is saying perform the sequence of operations on the given AVL tree. So both A and B are independent operations. Okay, so they are saying delete 4 and delete 7. So on this given AVL tree, so I have actually listed down this in the separate slide. So they are saying delete 4 then delete 7. Okay, and in another example they are saying delete 4 and then delete 2. So B is the example where they are saying delete 4 and delete 2. Okay, let's just do the first example, which means delete 4 and delete 7. Okay, so first delete 4. So if you delete 4, tell me things are getting imbalanced or things are same. So 2 is okay, there is no problem with the 2. 5 is also okay, right? What about 8? 8 is also, oh, this is interesting, right? See, if you delete 4, then no, 8 is also okay. Okay, no problem. If you delete 4, then yeah, 2 is okay, 5 is also okay, but you will not stop here. You will check till 8. So till 8 you will check. So 8 is also okay because this height is 4, this height is 3, right? This is 1, 2, 3, and right hand side height is actually 4. So there is no problem. So yeah, I mean you can say that height is 3 or 4 does not matter. Maybe you will say height is 2 for the left subtree only. You will say height is 2. Here the height is 3, 1, 2, 3, right? So that is why 8 is also balanced, no problem. So for deletion is very straightforward. Now let's delete 7. Okay, after deletion of 4, I need to delete 7. So let me do one thing. Let me just actually blur this, so you should not be able to see this 4. Okay, so this, just assume that 4 is deleted. Now let's delete this 7. If I delete this 7, tell me, is this 5 balanced? And this 6 is balanced? Yes, 5 is balanced. But I will not stop here. I will actually keep on going till the root. Okay. Now you see 8 is imbalanced. Why? Because this height was earlier, because of this like 1, 2, 3 height was there, or 2 height, whatever, right? But here now 1, 2, 3, and like if you include this also, 4 height is there, and here 1, 2 height is there. So that is why the balance factor is -2, right? So 8 is imbalanced. So after deletion of 4, nothing is imbalanced, but after deletion of 7, 8 is imbalanced. So let me do one thing. Let me just fix this 8, right? Okay. Now to fix this 8, you will choose whether it is in stick or elbow. So tell me, where should I go? 5 or 11? Obviously 11, because 11 is having higher height. Now tell me, between 10 and 12, where should I go? 10 or 12? 12, because 12 is having higher height, right? So that's why this is in stick. So let me quickly convert that to mountain. How? That's very easy. So this 8 is having this 5 as a left child, and then 2, 7, right? 2, 6, and then 12 is having this 13, 14, and then 15. One thing is remaining, 10, 9, right? 11 left, 10, 9, which means here 10 and then 9. Yeah, so this is balanced. So that is how you can delete 4 and 6. Very easy. Now let's go to this B, which is saying delete 4 and 2. So after deletion of 4, let me delete 2. So basically deletion of 4 is not causing any problem. Now let me delete 2. So in first part I have deleted 7 after deletion of 4. Now I want to delete this 2. Now if you delete this 2, tell me what are the things that got imbalanced? This 5 got imbalanced, right? So let's just fix 5. So which means I will just fix this 5 like this. I will let me just copy this. I think that will be easy. So let me go to the new page and let me fix this 5, right, which is 5 6 7. So you can actually delete all of this. You will say that to fix this 5 you will just convert this stick to a mountain, which is basically 6 5 and 7, right? That much easily you can convert that stick to a mountain, right? Now after this one rotation, should I stop or should I be doing something else? This is the thing that I wanted to emphasize here. Okay, tell me, after this one rotation should I stop? Obviously no, because in case of deletion it might so happen that this 8 height or 8 balance factor might got disturbed. Let's just see this height is 1 or 2, like whatever you want to say. So from here you are getting 2, and then from here you are getting 1 2 3 4, right? So you will say the 2 minus 4, which means minus 2. So basically, or you may say 1 minus 3, does not matter. Minus 2 is the balance factor for sure, right? So you will say that 1 minus 2 is actually the correct answer. 1 minus, let me just do 1 minus 2. So 1 minus 2, which means 1 minus 3. 1 minus 3, which means minus 2, right? So you will say that 8 is not balanced, right? So which means after deletion of 2, you are getting 5 as imbalanced, and then once you fix this 5, you got to know that 8 is also imbalanced. So now you need to fix this 8 also. Okay, so you just fix this 8. So this is from here you will go to this, and then this is having higher height, so you will go to this. So you can just fix this 8, which is very easy. 11 8 12, and then 8 is having this on the left side, it is having this as subtree, and this 12 is having very simple 14 15, and on the left side 13. 11 left side is 10 9, right? So left side 10 9. Yeah, so now this 11 is also fixed, right? This position also fixed. So that is how it is taking 2 rotations. Okay, it may take log n rotations. Why? Because you may keep on going to the root. Okay, see what is happening. Just observe here what is happening here, that this 8 is having height of let me just call it from this side 1 2 3 4, let me call it 4. Okay, it is having height of 4, and from here it is having height of 3, right? And then what you did, you have deleted this, that's okay. Now suddenly this height was 4, this height is 3, right? Or let me just be very precise actually. So this height is actually 3. I mean the subtree height is 3, right? So for the subtree you want to be counting this edge. So subtree height is 3, this height is actually 2, right? So suddenly what is happening, that the balance factor was minus 1, right? That's not a problem. But when you are fixing this 5, suddenly what is happening, this height has become 1, and then 8 also got disturbed, right? So like once you fix this all, then 8 is also getting disturbed. Now what may so happen, that you may keep on going till the root. Why? Because what may so happen, just consider the case where you will be doing something like this. See, this 8 balance factor got disturbed because it was having the, like, from the left subtree. Now earlier it was getting height of 2, and earlier it was getting height of 3 from here, and then now it started getting height of 1 only from here, right? So suppose 8 is also having some parent, where right subtree, so this is basically from here it is getting height of 4, right? From left it is getting height of 4, okay, and from right it is let's suppose it is getting height of 5, okay? So this subtree is having height of 5. Now what may so happen, that once you fix this 8, okay, what may so happen, that this height from like this node is basically getting height as a 4 height from the left subtree. From this perspective, just see that left subtree's height is just 4, right? So what may so happen, that once you fix this 8, okay, which is in the next slide I think. So once you fix this 8, height has become 1 2 3 only, right? 1 2 3. So once you fix this 8, height has become 3. So which means from this node perspective, this height, okay, which will become 3, and this height is still 5. So this node will also get disturbed, right? So that is why it may keep on going, and then it may keep on going from here also, right? Maybe this node is having the similar configuration where it is getting height of 6 here, and then say something like height of 7 here, right? So something like that can happen, and it can keep on going till the root. So you do not need to make the things complicate. complicated. You just need to understand that, like in case of deletion, you may keep on going to the root. Okay, so that's the thing. I hope you got it. That's very easy actually. Just you just need to identify whether it is stick or elbow using very simple rule and just keep on going to the root. So basically, in case of deletion, rotation may propagate to the root, which means there might be order of log n rotations. It is extremely important. Okay, I mean important in the sense like you should be knowing it. Okay, they may ask it, may not ask it. That's a different story. But you should be knowing it. I mean, it is not very easily accessible to every gate aspirant. I'm sure like most of the gate aspirant might not be knowing that what is what is the difference between insertion and deletion, and like they might not be knowing many things about the this AVL that we have discussed. Okay, so if you are studying from this lecture, then you should be knowing things very deeply. I hope you got it right. Now, for your sake of practice, what you can do, you can solve this question. Okay, I currently do not have an answer of this question, but you can solve this question, and you can solve this question for which I have answer in the next page. Okay. This is the answer of that question. So this question I have taken from University of Washington. You can solve this question. This question I have made by myself. You can try it out and comment your answer. Okay. So AVL tree deletion has been completed with this lecture. Let us now talk about minimum and maximum number of nodes of an AVL tree for given height h, which means that given height h, so they will give you that height is fixed to be h. Now, how many minimum number of nodes that you can put in this height h, or how many maximum number of nodes you can put in this height h, right? These are the two questions. So questions are like this: how many maximum number of nodes are possible in an AVL tree of height h? So height is fixed, okay? Height is fixed to be h. And then they are saying how many maximum number of nodes you can put in here. And second question is that height is fixed to be h, and how many minimum number of nodes you can put here such that the resultant tree is AVL tree. See, if it is generally BST or some binary tree, then you will say the minimum number of nodes that you want to put here such that height is h is like this, right? But if it is an AVL tree, then you cannot put a skewed tree. So that's why this problem becomes like quite interesting. Okay, so I hope these two questions are clear. Now let me walk you through the first question, then we will go to the second question, and these two questions will be like taking quite bit of time. So just go through this video completely. First question is saying that how many maximum number of nodes that are possible in an AVL tree of height h, which means that height is fixed to be h, right? And they are asking how many maximum number of nodes you can put in here. So what you will be doing, you will be starting with one node, and at every level you want to put maximum number of nodes, right? At every level you will say that okay, let me put maximum number of nodes. So this height is 0. So for let's suppose for height 3, how many you can put? This height is 0, this height is 1, this height is 2, this height is 3. So you will say for height 3 you will be putting every level you will be filling completely, right? So you will say that for height 3 you will go for 2 power 0, which is one node, plus 2 power 1 plus 2 power 2 plus 2 power 3. So for height 3 you will be putting these many nodes, which is actually 2 power 4 plus 1 minus 1, 2 power 3 plus 1 minus 1, which is 2 power 4 minus 1, which means 15. If you count these nodes, then it is 15. So if someone asks you that how many maximum number of nodes you can put in for height h, then you will say that for height h you will be putting, so for height 3 you are going from 2 power 0 to 2 power 3, right? So similarly for height h you will be putting from 2 power 0, 2 power 1 to 2 power h. So maximum number of nodes that you can put in height h is 2 power h plus 1 minus 1, isn't it? Which means given height is h, and now you want to put the maximum number of nodes in this height. So you will be doing what? You will be actually filling up all the levels, right? So this is just like a perfect tree. You will be filling up all the levels, and you will say, let me fill up all the levels because I want the maximum number of nodes, and for this height, so I will filling all the levels, which is like this. So the answer of this first question is very simple, which is 2 power h plus 1 minus 1. This is the answer. Now there is another way to come up with the same answer. Let me tell you that way. That way will help you to understand the second question also. Okay. So what is my objective? I want to find maximum number of nodes. So height is given height h. I want maximum nodes possible. right? Now that can be done by recursion also. How? Let's just see this. Suppose that this is your first node that you have in the AVL tree, and then this is your left AVL tree, and this is your right AVL tree. Okay, I mean left subtree and right subtree. Now since this is an AVL tree, now the balance factor of this could be either -1 or 0 or 1, right? Which means that if this height is h, then for the -1 balance factor, let me go to the next page. Suppose this is the AVL tree that you have for the height h, okay, and this could be -1, 0 and 1. Now if this height is h and these balance factor could be -1, 0 and 1, which means like there are actually a couple of possibilities that you already know. Like one possibility is that in the left subtree you can say height is probably h minus 1, and in the right subtree you can say height is this is h minus 1, this will be total h, right? So you can say height is h minus 2, and then here you can say height is h minus 2, and here you can say height is h minus 1, and the total height will be h only. So in this way the balance factor of this will be -1, isn't it? Second possibility could be, so I hope you're getting, see what I'm saying, that you want AVL tree of height h, right? And there are three possibilities, which means the balance factor could be -1, 0 or 1. So why I'm talking about the balance factor? Because I want to emphasize that on the left and right subtree what could be the possible heights. So first case is that this left subtree may be having height of h minus 2. Let me write it very clearly. This may be having height of h minus 2. Right subtree may be having height of h minus 1. Second possibility is that left subtree may be having height of h minus 1, and right subtree is also having height of h minus 1, and the total height will be h as it is given, and the balance factor in this case will be 0, right? Third possibility could be exactly similar to this, which means like left subtree, instead of left you will say that right subtree is having the lesser height, which is h minus 2, and here h minus 1, so such that the total height is actually h, because it is h minus 1 and this is one height, so you will say the total height is h, and then in this case the balance factor will be 1. So if you want an AVL tree to have height h, then there are three possibilities for the left and right subtree to have the heights. I hope this is clear. This has nothing to relate with the minimum number of nodes or maximum number of nodes, these kind of things. It is in general, right? Now let's come to the question. Question is saying we want maximum number of nodes, right? So in this height h, we want the maximum number of nodes. So you tell me which possibility is best suited for you. You want the maximum number of nodes to fill in. So you want to take the maximum height everywhere that is possible, right? Which means you will take this, you will take this, which means you will go for the second case of balance factor 0. Which means if you want an AVL tree to have maximum number of nodes of height h, right, then you will say that this is an AVL tree where the height is h, and the left subtree will be having height h minus 1, and the right subtree will also be having the height of h minus 1. Because we want to fill the maximum number of nodes. So why to take height lesser? Why to take h minus 2 anywhere? I will be going for this option. I will be saying that height should be here h minus 1, because I want to fill the maximum number of nodes. If height is more, which is h minus 1, then I will fill in the more nodes, right? I want to fill the maximum number of nodes. That is why I will go with this option. Suppose I want to fill the minimum number of nodes, which is the second question actually. So here I do have two questions. The second question is saying how many minimum number of nodes are possible. So I will come back to this question later. It is actually very interesting, but I will come back to this later. Suppose if they ask you to fill the maximum number of minimum number of nodes, then you will go with which option? You will either go with this option or this option. Actually both are identical, does not matter in my case. Okay, so let me say that you will go to this option. Why? Because you want to take lesser everywhere possible. So you will take h minus 2 if you want to fill minimum number of nodes. Why to take more heights? Because if more height is given, then you have to put more number of nodes, right? So if you want to fill the maximum number of nodes, you will go with this option. I hope this is clear to everyone. Which means I will say that my AVL tree of my interest will look like this. For the question 1, this is my AVL tree of my interest, right? Now, I hope why I'm drawing this tree, it is clear to everyone that the left subtree for the maximum number of nodes, left subtree and right subtree will be having height of h minus 1, and the total height is h, isn't it? Now, Let me define a term which is NH, which says that NH is maximum number of nodes, maximum number of nodes with height h. Okay, maximum number of nodes in AVL tree with height h. Basically, in AVL tree, I'm always talking about AVL tree in this lecture. In AVL tree with height h, isn't it? So NH is maximum number of nodes in an AVL tree with height h, which means I'm interested to find out this NH. Okay, what is this NH? And I will do it recursively. Actually, I know the answer. How? I know that NH is, if you can recall from our previous discussion, that NH is actually this, right? I know the answer, but still I'm interested to find out this NH in some other way. So this is the second way where I'm finding out this NH. I hope setup is clear. What is my setup? I want to find out the maximum number of nodes. Let me call it NH. NH is the maximum number of nodes with height h. And my tree will look like this, isn't it? Now tell me how many number of nodes will be here. See, I want the maximum number of nodes in the whole complete tree, right? In this complete tree, I want the maximum number of nodes. Now tell me, if I want maximum number of nodes in the complete tree, should I not be having maximum number of nodes here also and maximum number of nodes here also? Everywhere I will be taking the maximum number of nodes, right? Isn't it? See, I want in this complete tree, I want maximum number of nodes. So for that, what I will be doing? I will be putting maximum everywhere, which means I will be saying that I want maximum number of nodes here, I want maximum number of nodes here, isn't it? So can you tell me what are the maximum number of nodes here? I mean, what are the number of nodes here? Since I got the maximum number of nodes, I can use the same formula. I can say it is NH minus 1, isn't it? Okay, just understand this. What is NH? What is NH? NH is maximum number of nodes with height h, isn't it? Now I want the maximum number of nodes with height h minus 1, because here in this setup, here this height is h minus 1, here this height is h minus 1. I will be putting maximum number of nodes here also, then only it will be maximum, right? How can I put something lesser here? So I will be recursively putting maximum everywhere. So I don't worry about recursion. So for now, just understand like this. If I want maximum number of nodes to put in, let's suppose these are the two buckets, okay, of height h minus 1, and this is just one bucket of height 0 or something. Here I can just put one node, like this node, okay. I'm just trying to make you explain with this example, maybe it is useful. So here I'm just putting one node, and I want in these three buckets combinedly, I want the maximum number of nodes, okay. So you can say that, okay, I do not have any control on this bucket because it can just have one node. But if you want all of these three buckets combinedly, if you want maximum number of nodes, you will be saying that you will be filling maximum number of nodes here, maximum number of nodes in this bucket, right? Then only you can have total in these three buckets maximum number of nodes. So how many nodes you can put here? So maximum number of nodes with height h is nh. So it means that for height h minus 1, it is nh minus 1, isn't it? So which means that maximum number of nodes for this left subtree will be nh minus 1. Maximum number of nodes for the right subtree will be nh minus 1. And maximum number of nodes for this complete tree will be nh. Which means you can say that there is a relation between nh and nh minus 1 and these things. You can say nh equal to nh minus 1 plus nh minus 1 left plus right plus 1, isn't it? So is this okay to everyone? It is saying that nh, which is total number of nodes in these three things, are nothing but number of nodes here, and one node this, isn't it? Okay, so what I'm doing, let me again explain. I'm saying that nh is maximum number of nodes with height h, and these two are having height h minus 1. So that is why I can say that this will be having number of nodes at h minus 1, because I want maximum here, I want maximum here also. That is why I can say these will be having nh minus 1 and h minus 1 nodes, and this total has nh nodes. Now you have the recursive formula which says nh equal to nh minus 1 plus nh minus 1 plus 1, isn't it? Where nh is maximum number of nodes of height h. Maximum number of nodes of height h. Okay, so this is the formula that we are getting, which means it is 2 into nh minus 1 plus 1. Now let me write that formula. So nh is 2 into nh minus 1 plus 1. Now here in this formula you can see that there is a recursion. Why? Because this function or this nh is in the form of its nh only, right? Nh minus 1. Now whenever you have the recursive formula, you must be having the base case. So base case here is that what if height is 0, which means n0. N0 will be what? Can anyone tell me in the English? Using this language, maximum number of nodes of height is 0, right? It is maximum number of nodes with height 0. Height 0, right? Which means if you do not want any height, like this height is 1, if you do not want any height, if you want 0 height, then you can say the maximum number of nodes, or just like you can just only put one node, right? So it will be like this only. So n0 will be 1. What about n1? So n1 is, in English, can you tell me maximum number of nodes with height 1? So maximum number of nodes with height 1, can you tell me how it look like? With height 1, maximum number of nodes should be 3, right? So you can say n1 is 3, right? So n0, which is basically, let me actually draw a table, something like this. So maximum number of nodes with height 0. Okay, so number of nodes. Okay, let me write here height, with height. Okay, which means this is h and this is nh. This is maximum number of nodes, and this is how tree will look like. So this is maximum number of nodes with height 0. It means it will look like this n0. They are talking about n0. N0 will be just 1, and tree will look like this, isn't it? If the height is 1, then the maximum number of nodes you can have is 3, which means you can say n1 is 3. If height is 2, then you can say maximum number of nodes you can have is something like this. So 1, 2, 3, 4, 5, 6, 7, right? So n2 is 7. Like that you can keep on computing. But I do also have a formula which says nh equal to 2 into nh minus 1 plus 1. This is a recursive formula. And I know the answer. I know the answer early from the earlier derivation, that nh should be 2 power h plus 1 minus 1. Let me do one thing. Let me solve this formula. This is a recursive formula. We will see how to solve these formulas in case of algorithm. I will be applying the substitution, Master's theorem, and these things, right? So that is the part of algorithm. But for now, we can just unroll this and we can just find out the formula for nh. Okay. So nh is 2 into nh minus 1 plus 1. Okay. Now, what will be the nh minus 1? Can you tell me nh minus 1? So nh minus 1 will be 2 into nh minus 2 plus 1, isn't it? See, instead of h, just put h minus 1 everywhere. So if you put h minus 1 everywhere, you will be getting this, right? So which means you can say, okay, let me also write the nh minus 2. nh minus 2 will be, just put h minus 2 everywhere, which means 2 into nh minus 3, 2 into nh minus 3 plus 1, right? Now, what will be an h minus 4, h minus 3 also, like you can write h minus 3 also, 2 into an h minus 4 plus 1, right? Like that you can keep on computing nh, n minus 1, nh minus 2, nh minus 3, like that. Okay. Now coming back to this, can you just unroll this? This will be nh equal to 2 into, what is the value of nh minus 1? It is saying 2 into nh minus 2, 2 into nh minus 2 plus 1, and then plus 1. Isn't it? So it is coming out to be 2 square into nh minus 2 plus 2 plus 1. Now whenever, like, we will solve this in the algorithm, don't worry, we will solve this kind of substitution in the algorithm, but for now I'm telling you, whenever you have some series or something, do not add, okay? Don't add this to be 3, okay? Don't add this to be 3. Have some patience, just observe what is the series that is coming out to be. Don't immediately add. So let me not add it, okay? I will not add it. Let me just replace this nh minus 2 also first, okay? This 2 plus 1 is already there, plus 2 plus 1. I will not add this to be 3. Let me replace this nh minus 2 so that you can observe the pattern. So nh minus 2 is nothing but 2 into nh minus 3 plus 1, right? Now if you just unroll this, if you just multiply this to 2 square here, it will be 2 cube into nh minus 3 plus 2 square plus 2 plus 1. isn't it? So as you observe here, what is happening whenever it is this point, at this point you observe whenever you are unrolling just one time or two times, so it is saying 2 square into nh minus 2 plus 2 plus 1. Now here it is saying 2 cube 2 square 2 1, right? And here nh minus 3. In general, can you tell me what will the answer? In general, you can say it will look like this: 2 power k into nh minus k into nh minus k plus see, it is 3, then it is 2, right? So it will be 2 power k minus 1 plus 2 power k minus 2 till 1, right? Till 1. So this will be your final nh. Now let me write it on the next page. It is actually very easy. Like once you go through those algorithm questions of the substitution, it will look like, it will look like very small problem. Okay, so you will not even be picking the pen and paper to solve these kind of questions in case of recursive substitution. You will just tell me that okay, this should be the answer. You will be so much habitual after the algorithm questions. Okay, so anyway, for now this is 2 power k into n h minus k and h minus k plus 2 power k minus 1 plus 2 power k minus 2 plus till 2 power 0 or 1, okay, till 1. Now what if, now let me basically substitute this as a base case. What if h equal to k, which means I know the value of c. You can put k value anything. So okay, let me just put k equal to, you can put k value anything. You can put k value h, you can put k value h plus 1, or sorry, not h plus 1 because otherwise it will be negative. You can take h minus 1, h minus 2, like that, right? You can put any value of your choice. There is no problem at all. You should be just knowing the base case. Okay, let me put k value value h, then it will be, this will look like this: 2 power h into n0 plus 2 power h minus 1 plus 2 power h minus 2 till 1, right? If you are putting k value h, suppose you are putting k value h minus 1, okay, suppose you are putting k value h minus 1, so you will say 2 power h minus 1 into n. Now if you are putting h minus 1, it will be n1 plus 2 power h minus 1 means h minus 2 plus h minus 3 till 1, right? Now these two are actually same because this n0 is just can you recall the n0? N0 is 1, n1 is 3, right? So n0 is 1, right? So here it is 1 and then it is 2 power h plus, like that, and here it is 3. So you can solve this also, you can solve this also, everything is fine, so there is no problem. Let me solve this. If you want, you can solve this by putting 3, you will be getting the same answer. Okay, you can try it. So now let me solve for this, which means let me just because I know the value of n0, which is 1, so I will be saying it is 2 power h plus 2 power h minus 1. 2 power h into 1, but I have not multiplied by 1 because I know it is just 1, so it will be just 2 power h, right? So it will be 2 power h minus 1, 2 power h minus 2 till 1. Then the whole summation is 2 power h plus 1 minus 1, isn't it? So finally you are getting nh as 2 power h plus 1 minus 1. 2 power h plus 1 minus 1. And earlier also we know that nh is 2 power h plus 1 minus 1. So from both of these I am getting nh as 2 power h plus 1 minus 1, right? I hope you got it. So basically there are two formulas. There is just one formula, which is nh. You can say nh equal to 2 into nh minus 1 plus 1. And if you solve this, then also we got nh equal to 2 power h plus 1 minus 1, and we also got this thing directly. Okay, directly. You can prefer anyway, there is no problem. Why I have told you this long way? Because there will be some kind of questions where you will be needing the recursion. You should be knowing that how to think in form of recursion. Now you know that how to think in form of recursion, right? So it is saying like in this slide it is saying that how many maximum number of nodes are possible in AVL tree of height h. So I know this is the formula. We can also get the similar result using the recursion, which is like this, right? Which is actually 2 into nh minus 1 plus 1. Okay. Now let's solve this question. They are saying what will be the maximum number of nodes of height h, which means height is given to be fixed, which is h, and they are saying what will the maximum number of nodes you can fill in here. So you can apply the formula, which is nh equal to 2 into nh minus 1 plus 1, or you can directly apply the formula, which is 2 power h plus 1 minus 1. Let me do one thing. Let me apply this formula and let me apply that formula also. So let me solve using both the formulas. So let me use the first method, which is basically solving the recursion. Suppose I do not know this formula directly, I just know that nh equal to 2 into nh minus 1 plus 1, and they are asking for n5, right? They are asking what is n5. which means they are asking, see this nh is the maximum number of nodes of height h, and they are asking maximum number of nodes of height 5. So it means they are asking n5. So can you tell me what is n0? N0 was 1, and using this formula, which is nh equal to 2 into nh minus 1, nh minus 1 plus 1, can you tell me what will be n1? N1 will be 2 into n0 plus 1, which means it will be 3. What will be n2? It will be 2 into this, which is 6 plus 1, which is 7. What will be n3? N2 is this, n3 will be 2 into this, which is 14 plus 1, which is 15. What will be n4? It will be 2 into this, which is 30 plus 1, which means 31. What will be n5? It is 2 into this, which is 62 plus 1, which is 63. So we are getting 63 using this formula, right? Using this recursion. Now, can you tell me what if I apply this direct formula? Then also, this is the second method. Let me write it. This is second method. Then also, you will be getting the same thing. How? 2 power 5 plus 1 minus 1, which means 2 power 6 minus 1. It is 64 minus 1, which is 63, isn't it? So both are giving the same answer, and they must be giving the same answer, right? Because both are actually the same thing. Now you know that given a height h, how to fill the maximum number of nodes in an AVL tree. Okay, so let me solve this question. They are saying what will be the size of biggest AVL tree for the height h, which means height is fixed to be h. In this, you want to have a more more and more nodes, right? Because they are saying for the biggest AVL tree, right? So how to solve this question? You know that the formula is nh equal to 2 into nh minus 1 plus 1. Okay, or you can directly apply the formula, which is 2 power h plus 1 minus 1, which is 2 power 9 minus 1, which is 512 minus 1, which is 511, isn't it? 511 should be the correct answer. Or you can solve using this formula. They are asking for n8. So if you remember, then we have solved till n5. So n6 will be 2 into this plus 1, then 2 into that plus 1, like that. You can keep on calculating in the bottom of equation, and you will be getting 511 as a correct answer. Okay. Now till now we have seen that given the height, how to fill the maximum number of nodes. We can fill the maximum number of nodes if the height is given. And there is another way of saying, or another way of asking the same question. That is that they may say the nodes are given. They may say that okay, n is the number of nodes that you have, and you want the minimum height possible. See, these two are exactly same question of different way of asking. This is very intuitive. This is not much intuitive. That's why I'm actually explaining this to you, because they may ask in this way also. So first way is saying that height is given, height is fixed to be h, and then they are saying how many maximum number of nodes you can fill in here, right? Maximum number of nodes you can fill in here. This is the first way of asking the question. Similar question can be asked in this way. They are saying nodes are given. I mean, nodes are fixed. Okay, you do not have much nodes. You do not have unlimited nodes. And what is the minimum height possible with these nodes? Okay, see, if you want the minimum height for the given nodes, so let me explain you with the another example. Suppose that this example is given to you, and in this they are saying that height of these height with 6 bricks. So basically they are saying 6 bricks are given. Okay, number of nodes or number of bricks are given to be 6, and they are saying you want what? You want minimum height. Okay, if you want the minimum height, you will go with the first option or the second option. If you want the minimum height, you will be putting the bricks like this or like this. Suppose that on the surface at max 3 bricks can be put. Otherwise, you will put all the 6 bricks in a line, and you can say that okay, this is the minimum height possible, right? So suppose that I can only put at max, I can only put the 3 bricks. Then where you will be going? You will be going with this option with the minimum height. See, they are asking for the minimum height. 6 bricks are fixed. Number of bricks are fixed to be 6. Then how you will be arranging your bricks? Either you will be arranging like this or like this. Obviously, you will be arranging like this because you want the minimum height possible. Similarly, if number of nodes are fixed, suppose they say number of nodes are 15. Okay, this is fixed. This is fixed. Then they are asking minimum height possible with this. Minimum height possible. Then what you will be doing? You will be saying if you want the minimum height, okay, then you will be basically saying that you want to put the maximum bricks, right? See, here you are just putting one brick, but here you are putting the maximum bricks per level. Similarly, you will be putting the maximum number of nodes per level, which means if number of nodes are fixed to be 15, here you can put 1, and then here you can put 2, then here you can put 4. So you will be putting 4 only. You will not do any margin here. Okay, you will not say that okay, let me just put 3. Why? Like, why you will be doing it? So number of nodes are given to be fixed. That means 15 nodes you have. You want to apply those 15 nodes such that the height is minimum. So you will be putting everywhere maximum number of nodes, isn't it? See, I know it is counterintuitive. Actually, this is inversely proportional, which means height and nodes are inversely proportional. If you are using maximum nodes, then you will be getting minimum height. If you want the minimum height, you need to have the maximum number of nodes available. Okay, which means here they are saying that you have the nodes which are n, and you want the minimum height, which means you will put in the maximum number of nodes everywhere, isn't it? So if you put maximum number of nodes everywhere, you have 15 nodes. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yes. So with the 15 nodes, you can have minimum height. Minimum height you can have 1, 2, 3, right? Maximum maybe like I will come to that question later. But if you put this node here, then also it is an AVL tree. Then the height is 4, right? But you want the minimum height with these many nodes, so you will be putting like this. So if you want the minimum height, you will go for the maximum number of nodes per level. If you want the minimum height, if you want the maximum height, then minimum number of nodes. Obviously, see, if you want the maximum height, if you want the height to maximize, then you will put in just one brick. So if you want this height and nodes per level are actually inversely proportional. This is what I want to explain. Nodes per level. Which means if you want minimum height, you need to fill the maximum nodes per level. If you want the maximum height, you will be filling the minimum nodes per level. Okay. So just come back to this question. They are saying if height is given, if height is fixed, and you want to fill the maximum number of nodes, it is okay. I mean, it is understandable. But the similar question can be asked. They may say the nodes are fixed, nodes are given, and then you want the minimum height possible. If you want the minimum height possible, then isn't you are filling the maximum nodes per node? So aren't these two processes are same? Basically, first process is saying that fill the maximum nodes per level. Second process is also saying fill the maximum nodes per level, isn't it? See, they are saying nodes are fixed to be n, and then you want minimum height. So you will be doing what? You will be filling the maximum nodes per level. Let me explain you with some questions. Suppose that 15 nodes are given to you, and they are saying smallest possible height of the AVL tree. You know the formula of this. What is this formula? This formula says that NH is maximum number of nodes with height h, isn't it? In an AVL tree. Now what they are asking, 15 nodes are given to you. So basically they are saying these 15 nodes are maximum nodes, because you cannot have more than the 15 nodes, right? They are saying this 15 is given to you, and they are actually asking this h. Okay, they are asking this h this time. Earlier what used to happen? Earlier they used to give this h. They used to say, oh, okay, with the height 3, how many maximum number of nodes are possible? And they used to ask this n3. But here they are doing this reverse. They are saying that maximum number of nodes are 15. What is the height? And that height is actually the minimum height. Okay. So if 15 is the nodes that you have, then what could be the smallest possible height you can have? Now suppose you don't know that what is the height needed to consume this 15 nodes. Okay. So suppose, I mean, actually you don't know, but let me just write, suppose you don't know. What is height needed? What is the height needed to consume 15 nodes? Okay, so you want the minimum height. So basically, let's suppose this much height is needed to consume the 15 nodes. So what you do, just keep on throwing the nodes here. Okay, and let's just keep on incrementally adding the height, which means that let's just throw one node here. You will say, okay, till now height is 0. Now let's just throw more nodes here. Per label, let's keep on throwing the nodes. So till now you have consumed 3 nodes and height is just 1. Okay, I will calculate actually height later. So keep on throwing the nodes. Now you are throwing more nodes. You will say that okay, now the height has become 2. Okay, like that, keep on throwing the nodes. So basically, let me just write those numbers here. This n0 is actually 1. So here n is the maximum number of nodes for the height 0, right? N0 is the maximum number of nodes for the height 0. Now n1 is 3, n2 is basically twice of this, which is 6 plus 1 7, and then 15, then twice of this, which is 30, and then 31. Like that you can keep on doing, right? This is n3, this is n4. Now what I'm saying, if you throw one node, then you will be just filling. If you throw one node, you will be just filling 0 height. If you throw 3 nodes, you will be filling 1 height. If you throw 7 nodes, you will be filling 2 height. If you throw 15 nodes, then you will be able to fill the height of 3, which means if you want the height of 3, 1 2 height of 3, you need to throw 15 nodes, right? You need to throw 15 nodes. So if you are at the height of 3, then all of your 15 nodes will get consumed, which means if you have 15 nodes, then smallest possible height is 3. Actually, they are asking at what value of h it is becoming 15. So for that you can say the value of h is 3, for that it is becoming 15, which means if you throw 15 nodes, then the height will become 3, right? Now suppose they ask you that for the 16 nodes, what is the minimum AVL tree height possible? AVL tree height possible. Now what you will be doing, suppose this is the question. Now what you will be doing, you will say that you do not know the height, and then you will keep on throwing the nodes. If you just throw, let me just write the earlier equations here also. Let me just copy this. Okay, so if you just throw let's suppose 0 nodes, then if you just throw 1 nodes, then you will be filling the height of 0. If you throw 3 nodes, 7 nodes, 15 nodes, so you will say you have thrown, let's suppose till now you have got the height of 3, and you have thrown 15 nodes. So you have 15 nodes here, and you have everything, every level is full. Okay, here every level is full, and the 15 nodes you have thrown, but you have 16 nodes. You want to consume those 16 nodes, then you have to go for one more height. There is no other option. So you will say that minimum height that is possible for 16 nodes is actually 4. Okay, you're getting me? See what you did, you found out, what you can do, you can basically find out these things, and then you can say okay, 15 nodes are consumed till height 3, and then you have one more node. Okay, if you had, let's suppose, 16 more nodes, which means 15 plus 16 is actually 31. If you have total 31 nodes, then also you can say that okay, height is 4. But if you only have 16 nodes, then also height is 4. I hope you're getting. Let me solve one more question, and then I think it will be more clear. They are asking what is the minimum possible height of AVL tree with the 63 nodes. You have 63 nodes. Okay, let me for the sake of explanation, let me just do some other nodes, maybe 62 nodes. Okay, 62 nodes. So let me copy that here also. So here it is saying that if you have just one node, then you will be having height of 0. If you have 3 nodes, then you will be having minimum height of 1. 7 nodes 2, 15 nodes 3, 31 nodes 4, and then n of 5. Let me write it twice of this, which is 62 and 63, right? And then if you have 63 nodes, then height will be 5, which means if you have 63 nodes, then 63 nodes will be completely filling height of 5, and this height is 5. But you have just 62 nodes, then also you will be needing height of 5. Why? Because just removing one node will not make the height lesser, right? See, if you have just 31 nodes, then your height will be 4. If you have 32 nodes, then also height will be 5. 33 nodes, height will be 5, till 63 nodes, right? Height will be 5 only. If you have 62 nodes, then also height will be 5. Once you have 64 nodes, then you have to go for height 6. So they are saying minimum possible height. So you keep on throwing maximum nodes here, right? And if you throw 15 nodes, minimum height will be, you will be getting 3. If you throw 31 nodes, minimum height you will be getting 4. Like that you can solve this question. I know this is counterintuitive, but if you go with this way, and if you just understand this properly, then you will be able to solve this in the exam. Okay. Now let's solve this second question, which is saying how many minimum number of nodes are possible in AVL tree of height h, which means they are saying that height h is given to you, and here this problem is very interesting because here they are saying you want the minimum number of nodes. Earlier was very simple. Earlier we were the maximum number of nodes, so we were keep on throwing the maximum number of nodes per level. We were like just throwing the maximum number of nodes. But here we want the minimum number of nodes for the height edge. Suppose if this could have been the BST. For the BST height edge, okay, height edge, how many minimum nodes you need? Maybe like for height 1 you just need for height 0 you just need one node. For height 1 you need two nodes, right? For height 3 you need two. For height 2 you need three nodes. Like that for height h, maybe you will be needing h plus one nodes, right? For BST it is very easy, but for AVLT it is little tricky. Let's see how I can solve this problem. Suppose that this is one node in the AVL tree and these are the subtrees of this AVL tree. Now you can say that this height, like this valence factor could be -1, 0 or +1, right? You want to fill the minimum number of nodes everywhere. And if you remember, we had couple of options for these heights. We had one option is this h minus 1 h minus 1. This was the one of the option. Another option is h minus 2 h minus 1, or you can have h minus 1 h minus 1 h minus 2. Actually these two options are same, so let me just take one option only. Okay, so you have these two options, which means you can have equal h minus 1 h minus 1, or you can have h minus 2 one place and h minus 1 one place. Can you have h minus 2 at both the places? No. If you have height of this h minus 2, then the total height will be just h minus 1. But we want the height of 2 be h. That is why this h minus 2 is not possible. Now this is h minus 2, this is h minus 1. Is this more suitable for the minimum number of nodes, or this is more suitable for the minimum number of nodes? See, you want to fill this AVL tree with the minimum number of nodes, which means you want to fill everywhere minimum number of nodes. Then why to take more height? That is why I will go with this option only, which means I will say for my AVL tree, one of the subtree will be having height h minus 2 and one of the subtree will be having height h minus 1, such that the total AVL tree is having the height h, isn't it? Now let me define nh, this time nh as minimum number of nodes in height h. Minimum number of nodes in an AVL tree of height h. Okay, this is the minimum number of nodes in an AVL tree of height h. This is what I'm looking for. Okay, if you are getting confused with this nh, let me say it mh. I mean, n I have already used, so let me just use mh. Or maybe this m might be more confusing because it is m for minimum or maximum, you might get confused. So let me just have the consistency. Let me just write nh, but this nh is different from earlier nh. Earlier it was the maximum number of nodes. This is minimum number of nodes of height h. Okay, so let's just before I drive the recursive formula, let's just do it numerically. Suppose that you want height 0, and then what can you say? The minimum number of nodes here, just write it down, and then also write it down the tree, how the tree looks like. If you want the height 0, the minimum number of nodes, obviously 1 you at least need, and the tree will look like this, right? If you want height 1, then the minimum number of nodes, see, the tree will be this. See, earlier the tree was this because we wanted the maximum number of nodes, but here tree could be like something like this, right? So minimum number of nodes is just 2, and this is a perfectly like AVL tree. Now if you want height 2, then in that case, see, in this case you could also have like this. Okay, so you can have either this or this, does not matter. But if you want height 2, can you have this as an AVL tree? Can you have minimum number of nodes 3? No, right? This is not balanced. So this is the minimum requirement. I mean, you will be having 3 height 2, so you will be having at least this kind of a structure, and then you need to balance every node. So this was balanced. Let me just balance this. So basically you have to have this as a minimum number of nodes, which means how many minimum number of nodes you need? You need at least 1 2 3 4 nodes, isn't it? If you want height 3, then how many minimum number of nodes you need? See, if you want height 3, which means 1 2 like 1 2 3, this much height you need, right? So how many minimum number of nodes you need? Is this enough to have minimum number of nodes? No, because this is not balanced. So which is not balanced? This is not balanced. So you can balance it like this, right? So now this is balanced, and then only unbalanced node is this. So here it is having 1 2 3 height, here it is having 0. So let me have at least 2 height here, right? At least 2 height here. Now I think everything is balanced. So you can have 1 2 3 4 5 6 7, 1 2 3 4 5 6 7, yeah, 7 nodes, right? So for height 3 you will be having something like this structure. Okay, so you can draw that structure on that page also. Let me just copy this structure on that page, so you can draw something like this here, and then you can say that the minimum number of nodes were 7, isn't it? So that is how you can find out the minimum number of nodes. But I will not be keep on doing this, right? I mean, I should be having some formula. So let's drive some formula for that. So basically what I want the minimum number of nodes everywhere, right? I want the minimum number of nodes everywhere. So I can say that this height is h minus 2, this height is h minus 1, such that the total height is h. Now nh is minimum number of nodes in height h. Now you want the minimum number of nodes here. So won't you be putting the minimum number of nodes here and minimum number of nodes here? Won't you be doing this? Obviously you will be doing this. Why? Because you want the minimum everywhere. You cannot put maximum number of nodes here, or you cannot put some arbitrary number of nodes here. You have to put a minimum number of nodes here and minimum number of nodes here, then only the total number of nodes will be minimum, isn't it? See, it is just like a bucket. I have 3 buckets. Okay, in this bucket there is only 1 node that is fixed. Now you want total to be minimum, number of nodes to be minimum. Want to be putting minimum number of nodes here and minimum number of nodes here? Obviously, right? So basically, if nh is minimum number of nodes of height h, then what will be minimum number of nodes here in h minus 2? You will be saying nh minus 2, and here it will be nh minus 1. Now, can you drive me the recurrence formula? Yes, it is right if you are thinking about this, which is nh minus 1 plus nh minus 2 plus 1. Okay, which is nh is saying nh minus 1 plus nh minus 2 plus 1. So what this formula is saying, that nh is minimum number of nodes of height h. To have that, I will be having minimum number of nodes in the left subtree, minimum number of nodes in the right subtree, and then I will be adding 1 for the root, right? So now I have the formula, which is nh, that is actually equal to nh minus 1 plus nh minus 2 plus 1, where nh is minimum number of nodes of height h, isn't it? I hope you got it. Earlier I had this formula, which is nh equal to 2 into nh minus 1 plus 1, that was for maximum number of nodes. Earlier, fortunately, I also had the closed form. I mean, closed form means I have the direct formula. Earlier, fortunately, I had the direct formula, but this time I am not having the direct formula. And this kind of recurrence is not easy to solve also. I mean, exact is not easy to solve. So I will not be solving for the direct formula. So this is the recurrence on which we will be working with. Okay, let me give you some examples. So minimum number of nodes are required for AVL tree of height h is this, recurrence is this, where nh is minimum number of nodes in an AVL tree of height h. Now you know the base case, which means if you have the height 0, then minimum you need 1 node. If you have height 1, then minimum you need 2 nodes, right? You do not need 3 nodes. Why to unnecessarily have 3 nodes? If you want to have minimum number of nodes, then why to unnecessarily have 3 nodes, right? So minimum you will be needing 2 nodes. Now you see here n0 is 1 and n1 is 2, and in general you can say nh is equal to 1 plus nh minus 1 plus nh minus 2, right? So nh minus 1 means number of nodes, minimum number of nodes in h minus 1 subtree, and minimum number of nodes in h minus 2 subtree, and then I will be adding 1. That is how you can find out minimum number of nodes of height h. Now let's do some question. How many minimum and maximum number of nodes of AVL tree of height h are needed? Okay. So let me first find out the minimum number of nodes. Minimum nodes for height h. So here you will be saying, if you want the minimum nodes, so I will be following this formula. plus nh minus 2, right, plus 1. Now they are asking for height 5, which means they are asking for n5. Now, do you recall this formula is somewhat similar to Fibonacci formula? I mean, if you know about the Fibonacci series, it is okay. Otherwise, like Fibonacci series basically adds earlier to number, and that is all. I mean, this formula is also adding one, but that's okay. So let me basically do one thing. Let me find n5, which means n0 I know is 1, and 1. So the series will look like this: n0 is 1, and 1 will be 2, right? You need a minimum of 2 nodes for the height 1, and then n3 will be just summation of these two and then plus 1, which means 1 plus 2 and then plus 1, 3 plus 1 4, and then 4 plus 2 like this is n0, this is n1, this is n2, and then 4 plus 2 6, and then 7, 7 plus 4 11, and then you have 12, 12 plus 7 19, and then you have 20, 20 plus 12 32, and then you have 33, something like that, right? This is 3, this is 4, this is 5, this is 6, something like that. So it is n0, it is n1, it is n2, n3, n4, n5, n6. They are asking for n5, so you will say 20, which means that for the minimum height of just 5, you need 20 nodes, which means why I'm emphasizing so much. See, if you just keep on doing this, if you just add these two, it is 3 54. If you just keep on doing this, it will be 8 8 88, and then it is increasing exponentially, isn't it? See, it is increasing too much. It is not increasing just by a factor of 2 or 3 like that, which means like this is 7, this is 8. It is saying that just for an AVL tree of height 8, you need minimum of 88 nodes, which is too much, isn't it? See, if you need AVL tree, if you need BST of height 8, you might be needing 9 or 8 or 9 nodes, right? If you just need BST of height 8. But if you need AVL tree of height 8, then you will be having 88 nodes there. And the more you progress, the number of nodes are increasing. So basically, just for height 8, it is a huge AVL tree. Okay, 88 nodes you will be having, almost similar to perfect tree, right? Almost similar to perfect tree, but it is not obviously perfect tree because you are not fulfilling all condition of perfect tree. So just to have 8 height, you will be having 88 nodes. This much difference is there in AVL tree and BST. I hope you got it, right? So here they are asking for the minimum number of nodes of height h. Then you can apply this formula. Using this formula, you want n5. So actually I have calculated n0, n1, n2, n3, n4, n5. So you can stop here. Then otherwise, just to observe, you can keep on going till 7 8. Okay. Now this minimum is done, and then they are asking maximum number of node. For the maximum number of node, I will be applying different formula. What is that formula? Formula is this for the maximum nodes. Okay, so for the maximum nodes of height h, formula is this: 2 into nh minus 1 plus 1. Here the base case n0 is again 1, and n1 here is 3, right? So let me do one thing. Let me find okay, so n0 is 1. Now you can just multiply by 2 here and then add 1. 2 into 1 2 plus 1 3, 3 into 2 6 7, 15, and then 31, then 63, then like that, so on, right? So you can say n0, n1, n2, n3, n4, and they are asking for n5. So like maximum number of nodes you can have 63, which is actually just like a perfect tree. So you can say the maximum number of nodes for the height h, for the height 5 is 63, maximum number of nodes is 63, and minimum number of nodes is 20. Okay, so just by using 20 nodes you can have an AVL tree, but if you want a perfect tree, you will be having 63 nodes. So do you remember when I have taught in the motivation of AVL tree? So there was some very strong condition in the motivation, that the last condition, it was saying that okay, like every node should be having the same number of nodes and same number of height, right? If I go with that condition, it will be a perfect tree, and it will be a too much restricted, right? It will be having 63 nodes. Otherwise, I could have worked with just 20 nodes to have height 5, right? So that's the benefit of AVL tree. I hope you got it. Now, as you see here, that for n2 I can have this kind of tree which is having minimum number of nodes of height 2, and if you want height 3, then this is the AVL tree with the minimum number of nodes. If you want height 4, then this is the AVL tree of minimum number of nodes. If you want height 5, similarly you can keep on doing it. If you want height 5, then you have the height 5 AVL tree which is having a minimum number of nodes. Okay. Now height is given and you can find the minimum number of nodes, which means least number of nodes we can fill in the given height. That's what we have just solved. Now let's go for the different question, actually the same question but different way of asking. So if you remember, I have told you that nodes per level and height are actually inversely proportional, right? Nodes per level. So instead of saying that height is given, they may say that nodes are given, which means that they may say that okay, you have 20 nodes. Okay, you have 20 nodes and you want to reach to maximum height that is possible. I mean, just use minimum number of nodes everywhere. See, it is just like analogous to the brick example where okay, maximum height or minimum height does not matter. So you want the maximum height. Okay, so you want the maximum height. So basically, you will be saying that you will be putting the minimum bricks everywhere. If you have 6 bricks, then you will go with the option 1 because you will put in the minimum bricks everywhere, right? Now let me solve one example and after that it will be more clear. Suppose that 12 nodes are given to you and they are saying the maximum possible height. So you have 12 nodes, you do not know what is maximum possible height. You will be saying okay, I will be throwing nodes here, but at every level I will be throwing minimum number of nodes because I want to reach the maximum height, isn't it? At every level you will be throwing the minimum number of nodes. Oh, okay, just one node won't be enough because it is not BST, but you will be filling with the minimum number of nodes such that you can reach the maximum height. Okay. Let me actually write that series, which is basically this one, which says 1. Okay, this is for maximum. This is 1 2 4 7 12. Okay, let me just write this series, which is 1 2 4 7 12. Actually I can just add these two and then plus 1, then 20, then 33, then 54, like that, right? So I will be doing what? I will be just putting, so it says okay, it says that this is n0 equal to 1. This means, let me write here, n0 equal to 1 means that for these are the number of nodes, right? For minimum of, I mean, if you have just one node, then you can have maximum of 0 height. If you have 2 nodes, then maximum of 1 height you can get. Okay, if you had 4 nodes, then okay, if you have 2 nodes, then maximum of 4, sorry, if you have 4 nodes, then maximum of 2 height you can get. If you have 12 nodes, so basically let me keep on filling. Okay, if you just throw one node, you will be getting this height. If you throw 2 nodes, you will be getting height of 1. If you throw 4 nodes, you will be getting height of 4, height of 2. So till now 4 nodes are consumed. If you throw 7 nodes, right, if you throw 7 nodes, you will be getting height of 3. If you throw 12 nodes, then you will be getting height of 4. Okay, this is maximum possible height possible. So if you throw 12 nodes, then you will be getting height of 4. Basically they are asking this number. Now they have basically told you that this NH is 12, find out this H. So you just tell me that how many nodes you will be throwing such that the height is maximum. So basically if you throw 12 nodes, then you will be having 4H height, isn't it? What if you throw 13 nodes? See, if you throw 20 nodes, which means, see, it is n4 equal to 12, n5 is equal to 20. So if you throw 12 nodes, then maximum height you will be getting 4. If you throw 20 nodes, then the maximum height you will be getting 5. But what if you just throw 13 nodes? Just see this in example. Let me just show you with this example. See, here if you are throwing 12 nodes, then you will get 4 height, right? So 12 is minimum number of nodes, right? 12 is minimum number of nodes to get height 4. And 20 is minimum number of nodes. See, this NH or N5, right? This is just 20 or whatever, right? This is minimum number of nodes, which means this is minimum number of nodes. These two are same, these two are equal, right? Which means if this is minimum number of nodes, then this is also minimum number of nodes. So this is 20 is minimum number of nodes to get height 5. Now if you throw 13, then what will happen? You will still be getting height 4 only, because you need minimum of 20, right? So earlier, let me write here, this is for minimum or maximum. Let me write minimum here, minimum formulas, and let me write maximum formulas here. So earlier what was happening, for in case of minimum, n4 is 12 and n5 is 20, and earlier in case of maximum, I think n4 was 31 and n5 was 63, right? So it is maximum number of nodes maximum number of nodes to get height 4. If you throw one more node, you will be getting height 5, right? See, this is maximum number of nodes for to fill this height 4. So for 32, just by increasing one, you will be increasing height 5, right? So this is saying that for 31, for height 4, you can at most fill 31 nodes. This is maximum number of nodes. Here it is minimum number of nodes, minimum number of nodes. Now if you just increase this by 1, which means if you say 13, then you will not be having height 5, because minimum number of nodes, minimum nodes for height 5 is 20. Minimum nodes for height 5 is 20. If you have 13 here, then minimum nodes, if you have 13 here, then it will not increase the height. Why? Because you will be able to accommodate this one node, one extra node in the height 4 only. You cannot go with the height 5. You cannot go with the height 5. So this is height 4, 1 2 3 4. You cannot just increase the height 5 with one node. If you do that, then this node will be unbalanced, right? This node will be unbalanced. If you try to increase one more height, then only one possibility, that you have to add this node here only, right? Can you add here and you can increase height? No. So you can add here only. But if you add here, then there will be a problem of imbalancing, right? So that is why you will say that here in this case, if you increase the number of nodes, then it won't increase the height. But here in this case, if you just have 32 nodes, then it will be increasing the height. I hope you got it. Okay, because 31 is the maximum nodes that you can have for the height 4. If you have 32, then you have to go for the height 5. Now this 20 is the minimum number of nodes for height 5. Whatever is less than 20, maybe 13 or something, right? So something like that, that will not go to height 5. I hope I'm clear in this. Now let's solve this question. They are saying what is the maximum possible height. So if they are saying what is the maximum possible height, then it means we need to apply the minimum nodes formula. Minimum nodes formula, right? And they have given 20 nodes. So the formula is this: nh equal to nh plus nh minus 1 plus nh minus 2 plus 1. And they have given this nh value to be 20. And they are asking for the value of h. Now can you find out? I think we can find out. For that, the answer will be, I think, 5, right? So the answer will be 5. You can easily do it. What if they give 21 instead of 20? They give 21. Then also answer will be 5, right? What if they give, let's suppose, let me edit. This is 32 and 33. Okay, so 33. So what if they give 21? What if they give 22? What if they give 23? Like that till 32. If they give till 32, then answer is 5 only. 5 only. Why? Because minimum number of nodes for height 6 is required 33. So this is minimum number of nodes you need. Minimum number of nodes to reach height 6, you need 33. You cannot have 30. You cannot have height 6 with 23 nodes, 22 nodes like that, right? Even if they give the number of nodes to be, let's suppose, 21, 22 like that, then also the answer is 5. I hope that is clear to everyone. Now let's solve this last question, which is a gate question. They are saying what is the maximum height of an AVL tree of 7 nodes. So they are saying maximum height, which means you need to go for the minimum nodes formula. So whenever they give the height, you just convert that to the corresponding formula. So minimum nodes formula. Minimum nodes means nh equal to nh plus nh minus 1 plus nh minus 2 plus 1. And they are giving this 7 nodes, which means they are saying this nh value is 7. Now you need to find out the corresponding answer. So basically, if the 7 is given, what is the series? Do you remember the series, or I can easily draw the series? Okay, this is n0, n1, n2, n3. So if 7 is given, then n3 will be the answer, which means you will say that 3 is the answer, right? Now what if they give 8? Then also 3 is the answer. What if they give 9? Then also 3 is the answer, right? Even if they give 7, 8, 9, 10, 11, then 3 is the answer. Why? Because for height 4, minimum number of nodes that you need is 12. So even if they give these numbers, then also 3 is the correct answer. I hope you got it. Okay. So there is one last question. If you want, let me do it. What is the size of smallest AVL tree with the height h? So they are saying height is given to be h this time. Okay, so which means they are saying height is h, and they are asking for the smallest AVL tree. So smallest here in terms of number of nodes. Why? because like generally in graph theory or in the trees, whenever I say the size of the tree or size of something, then size is measured in terms of nodes only. Okay, so smallest AVL tree means that for height 8, what is the minimum number of nodes possible? So you can apply this formula. Minimum number of nodes for height 8 they are asking, so you can apply this formula. They are asking for n8. So you know the series, I think 1 2 4 7 and then 12 and then 20, right? This is 0 1 2 3 4 5, and then you can keep on adding 6, and then you can just add these two, which is which 54 88, like that, right? 6 7 8. Okay, so I think 88 is the answer. 88 is the answer. So this is gate PYQ. I do not remember the year, but it is gate PYQ. Okay, so this much easily you can solve these questions. So do not apply much of the tension. Okay, do not get worried. Whenever they say number of nodes are given to you, then it means n of h is given to you. N of h is given to you, 7 8 or something, and then they are asking for the maximum height, minimum height. Based on that, take the inversely proportional. If they are asking for maximum height, take the minimum number of nodes formula. If they are asking for minimum height, take the maximum number of nodes formula. That's how you can solve these questions. Okay. Now let's solve one very easy question about AVL tree, which says that find the number of AVL trees. Find the number of AVL trees. Which means, like, for a given height, let's suppose height is given to you, which is suppose h, and you need to find all the AVL trees of height h. Okay. For example, if height is given to you as 0, then how many AVL trees are possible for 0 height? Only one AVL tree. What is that AVL tree? Just a root node, isn't it? So for height 0, just a root node is possible. So you will be saying that number of AVL trees for height 0 will be just 1. What about height 1? For height 1, how many AVL trees are possible? You will be saying for height 1, either you can have this kind of AVL tree, or you can have this kind of AVL tree, or you can also have this kind of AVL tree. So how many AVL trees are possible for height 1? You will be saying that 3. Now you might say that these are just structures. I mean, like you may also fill the elements in some different order, which means that given one structure, suppose this structure is given, then you may fill number of elements in the different order, which means let's suppose there are only 2 elements that you have for this structure 1 and 2. Can you fill this 1 and 2 in two ways, 3 ways, like that, or there is just one way? There is always one way. Why? Because AVL tree is also an BST, and BST, for a given BST structure, you can always fill in only one way, because the in order of BST is sorted. So if you just see that 1 can be here and 2 can be here, right? So if I ask you the number of AVL trees, then you just need to answer me number of structures. Basically, you just need to answer me how many structures are possible. If you are saying that 3 structures are possible, I will say that 3 AVL trees are possible. Why? Because every structure can only be uniquely filled. Okay. Now, for example, suppose that if I'm filling every structure in 2 ways, then the number of AVL trees will be 3 into 2, which is 6. Why? Because suppose I am filling this structure in 2 ways, this structure in 2 ways, this structure in 2 ways. Somehow, suppose I am filling like that, the number of AVL trees will be 6, because number of structures into the number of ways I am filling the AVL tree. Right? But here, in this case, the number of ways in which I can fill one structure is just 1. So that is why I will be just doing 3 into 1, which is just 3. Which means I am saying that number of AVL trees are possible is exactly same as number of structures possible. Because every structure is just producing me one AVL tree. It is not giving me multiple AVL trees. This structure will just give me one AVL tree. Why? Because if I have 2 nodes, I can just fill only in one way. Suppose I have 1 2, these 2 nodes. Now I can only fill these 2 nodes in one way. How? You will be saying that 1 will be coming here because in order is sorted, and 2 will be coming here, right? So to find the number of AVL trees, you will be just finding the number of structures. I hope the problem is clear to everyone. Now again, going back to the same question, for height equal to 2, how many AVL trees are possible? You may say that for height equal to 2, this AVL tree is possible, I think, and maybe this AVL tree is also possible, because is this balanced? Okay, this is not balanced, so you may say that this is not possible, but yeah, this is possible. So this is balanced, I think. 1 2 3, yeah, 1 2, and yes, this is balanced, this is balanced, this is balanced. So these two are possible. Maybe this is also possible, where you can say that this node, maybe you can have it here, right? So here if you have it, you will be having every node as balanced. So this is also possible. Maybe some other structure is also possible. Maybe you can say this is also possible, right? Now there could be many different structures which are possible for height equal to 2. So for height equal to 2, I think 1 2 3 4, and let me just figure out if there is any more structure I'm missing. So I think I'm missing one structure, which is this, right? So you can also have this kind of a structure. Is this balanced? Yes, this is also balanced. So I think there are actually multiple AVL trees are possible for height equal to 2 only. So just for height 2 you have multiple AVL trees. Now my question is that how many different AVL trees are possible for height h? Okay, I hope problem is clear to everyone. Given a height which is h, I want to find number of different AVL trees are possible. This is a question, but this question is actually little tough. So let me just simplify this question in some other wordings. Instead of finding out a number of different AVL trees for height h, let me find out. Let me pose a different problem to you. And the problem is that for given height h, instead of finding out number of different AVL trees, let me find out number of different minimal AVL trees. Now, what do I mean by minimal AVL trees? Is basically minimum number of nodes, minimal AVL trees. Which means if I say that for height h equal to 0, how many minimal AVL trees are possible? Just one, right? For height h equal to 1, how many minimal AVL trees are possible? Just 2, not 3. See, earlier it was 3, earlier it was this, because I can have any possible AVL tree for height h equal to 1. But here I am saying minimum number of nodes. So if you remember, we have already done this minimum number of nodes computation in the last lecture, but that is okay. Like that problem is not going to, we are again going to solve. This is a complete different problem. But if you want, you can borrow some idea from that lecture, that for the whenever I am saying minimal AVL tree, then it means I am asking what the minimum number of nodes in the AVL tree. Okay. So if there are 3 AVL trees are possible, I am rejecting this third possibility because I am only looking for minimal AVL trees. If I ask like for h equal to 1, how many minimal AVL trees are possible, you will just say 2. For h equal to 2, if I ask how many minimal AVL trees are possible, you might say like this is one minimal AVL trees. This may be okay. Maybe you can have something like this. This is one for height h equal to 2, and what else you should be having? So I can also have this node at this point, which means instead of saying this, I can also have this as an AVL tree. I can also have, like, let me fix this structure and let me just vary this node configuration. So I can also have this kind of structure. I can also have this kind of a structure. So for here left right I have done, here only right is done. So I can also have this kind of a structure, right? For h equal to 2, 4 minimal AVL trees are possible. What about total number of AVL trees? It might be more. So total number of AVL trees will be having this, will be having this, will be having this. 1 2 3 4 5 or 5 I have listed, maybe more, right? So I think I have not listed every possible AVL tree here. So maybe more, maybe something like this. I think I have not listed this possibility here. So total number of AVL trees might be many more, but I am only interested in minimal AVL trees. So whenever I am saying minimal AVL trees, it means I am saying a AVL tree which is having minimum number of nodes. For height h equal to 2, these are the minimal AVL trees are possible. So if the problem is clear, then let me actually define this problem very formally. Till now I have just given you the intuition that what I mean to ask. Okay, so let me say that nh is a number of AVL trees, number of minimal AVL trees, which means I am saying that for height h, these many number of minimal AVL trees are possible. Now if I ask you what is the value of n0, you will be saying minimal AVL trees for height h equal to 0 is just 1. If I ask you what is the value of n1, which means these are the minimal AVL trees for height h equal to 1. So these are the 2 minimal AVL trees are possible, right? For this value will be 2. And if I just ask you what is the minimum AVL trees of height 2, then you will be saying that I think there are 4 structures are possible, right? So this is fixed, and then you will be having like either on left or on right, or on left or on right, right? So these are the 4 structures possible. So you will be saying that n2 is 4. Otherwise, like if you ask how many total AVL trees are possible, these are much more. But I'm only interested in the minimal AVL trees. So I hope the problem is very much clear, right? Now coming to the very formal definition. So you will be saying that NH is the minimum number of NH is the number of different shapes of minimal AVL trees of height h. So this is minimal AVL trees, which means NSH is number of minimal AVL trees of height h, right? Now, how many minimal AVL trees are possible? This is my question. So, for that, let me just ask you this: for height 0, 1, 2, 3, how many minimal AVL trees are possible? This is for height h equal to 0. This is for height h equal to 1. This is like we have already solved for height h equal to 2. These are for height h equal to 2, and similarly we can also solve for h equal to 3 and so on, right? But we need some formula. Like we cannot keep on doing this numerically. We need some formula to drive the minimal AVL trees, which is given by our number, which is NH. Okay, let's just see how we can solve this formula. See here, this is NS0, this is NS1, this is NSH. So what do I mean by NSH? This is a minimal number of AVL trees with height h. So if I want minimal AVL tree, that means once I will be looking for h minus 1 and at another subtree I will be looking for h minus 2 height, right? This is what we know from the earlier lecture. That if I'm looking for minimal AVL trees, then either I'm looking for this kind of a structure or I'm looking for this kind of a structure. Tell me, am I looking for this kind of a structure also? This kind of a structure where I'm saying this height is h minus 1 and this height is also h minus 1? No. Why? Because this is not about the minimal AVL trees. Like this will not lead to a minimal AVL tree, right? So either I'm looking for this structure or I'm looking for this structure. Now tell me how many this kind of structures are possible. And once I have this number, I will just multiply by 2 because this structure is just a mirror image of this. I mean, like I can just swap this and this, right? I can just swap these two and I can have this. So instead of finding both together, let me just find one. Let me just work with this one, which means I will be just working with this one. And then whatever number I will be getting, I will just multiply by 2 because for every this kind of tree, I also have this kind of tree, right? So what I'm going to do, I want to find this NSH, which is minimal AVL trees are possible. So number of AVL trees I'm interested to find out, but I have restricted my problem to only minimal AVL trees, right? Now I know that I'm interested in finding out this kind of structures. So how many this kind of structures are possible? Suppose this is h minus 1, then this is h minus 2. I'm only interested to find out this kind of structure. What about other kind? Which means what about this kind of structure? Maybe this height is h minus 2. Maybe this height is h minus 1. Why I'm not encountering this? Why I'm not taking this into consideration? Because once I find this, I will just multiply by 2 and I will say that total minimal AVL trees are, let's suppose these kind of structures are 10, then I will say total minimal AVL trees are 20. Because for every this kind of structure, I can have this kind of structure, right? For every this kind of structure, I can just swap this left and right, and I can say this kind of structure is also possible. So that is why I will be only working with one kind of structure, just to make my problem simpler. So I hope the problem is very much clear. Now I want to find out total this kind of shapes. Okay, let's just forget about everything. Let's forget that we are studying data structures. It's a very much combinatorics problem where I want to find out the total structures are possible of this kind. Can you tell me? See, this height is h. Now I am saying you that NSH's total structures are possible with height h. Can't you just apply the recursive formula? Yes, we can do that. I will be saying that for height h minus 1, how many AVL trees are possible? This is NSH minus 1. For height h minus 2, if NSH is for height h, then for height h minus 1, it will be NSH minus 1. For height h minus 2, it will be NSH minus 2, isn't it? Now, you have everything ready. Now you just need to make it in a formula. How we can do it? Let's just see. See, this is NSH. Let me write it here. This is NSH, which is equal to this NSH minus 1 into NSH minus 2. It is not plus here. Why? Because if you just fix this, let's suppose for h minus 1 there is some structure. For h minus 1 you are fixing some structure, then for every of this structure there are NSH minus 2 structures are possible on the right side, isn't it? Here you will be applying the product rule, you will not be applying a sum rule. So from the combinatorics you must be knowing this, that why the product rule is applicable here, because for every of this structure there are NSH minus 2 structures are possible. So you will say that for every, let's suppose here, if you are fixing just one structure, let me do one thing. Let me take a very minimal example of height, maybe of height 3 or something like that. Okay, so let me say that this structure is there. Let me have this kind of a structure. Okay, so for every of this structure on the left hand side, there are, on the right hand side, there are NSH minus 2 structures are possible, isn't it? How? Like, you just fix this structure and you will be saying that for height h minus 2, either you can have this, so this is 1, right? Or you can, or instead of this you can have this, something like this, right? This is 2. So for every this left hand side of the subtree, you will be having NSH minus 2 of right hand side of subtree, which means for NSH minus 1 subtrees on the left hand side, on the right hand side you will be having NSH minus 2 subtrees. That's why I'm multiplying, I'm not adding. There is no point in adding, right? So NSH equal to NSH minus 1 into NSH minus 2. This is our final formula. Now you might be wondering that where I have encountered, where I have basically considered the case of these two subtrees, I have only counted for this subtree. Yes, you are right. So I need to actually multiply by 2 here. Why? Because for every of this, a pair is also possible. That is why I am multiplying by 2. So the final formula is looking like this. See, this is my h minus 1 structure, this is my h minus 2, right? This is my h minus 2. So this is height h, and the final formula of NSH is looking like this, where I am saying NSH equal to 2 into NSH of minus 1 into NSH of minus 2, right? This is my final formula. And what are the base cases? Base case will be something like this. For NS0, I know it is just 1, because for height 0 it is just only one possibility. For height 2, I can have height 1. For height 1, there is how many possibilities? 2 possibilities, right? These 2 possibilities. So I can say these 2 possibilities are there. Now, what about for height 3, or what about for height 2? Can you find out the height 2? Yes, we can easily do it. So let me write down for height 0, which is 1. For height 1, it is 2. What about for height 2? For height 2, you can just multiply these 2 and multiply by 2 also. Then it will be 4. For height 3, it will be, so you know this from the example also, right? We have already computed that ns2 is equal to 4. And you know how those 4 structures look like, right? And from the formula also we are getting the same thing. So those structures look like this, this, and this, right? And from the formula also we are getting the same thing. Now for height 3, you will be saying just multiply these 2, which is 8 into 2, which is 16. So for height 3, you will be having 16 minimal AVL trees. So that's how you can compute for any height. Let's suppose you want to compute for height 10. Then what you need to do, you can just fill out in the bottom up manner, which means just compute for 0, 1, 2, 3 till the 10, and then you will be having the value for NS10. I hope the problem is very much clear. Actually, this problem is like, they have not asked this kind of problem in the gate, but they may ask, and this problem is just there to make you think in terms of recursive manner, that for any binary tree or any AVL tree or something like that, how to think in terms of recursive manner, right? So that's why this problem becomes more interesting. Now we have covered everything about the AVL tree. Let me quickly summarize that what are the possibilities and what are the different components that we have studied in the AVL tree. So in the AVL tree, we have seen how to search. It is very much easy. This is exactly same as BST search. And how much time it takes? So it will be taking, so for BST search, it just take, in worst case it may take order of height, right? So in AVL tree, height is always log n, so it will be taking order of log n, right? Okay. Second thing is how much time it may take for the insert, or how to do insert. So it is same as BST insert plus balancing. So since I know that balancing is just going to take the order of 1, because balancing, I have shown you the course that it is just a pointer manipulation. So for BST insert, it may take order of height, and height in this case of the AVL tree, it is just always log n. So here also order of log n, right? What about a third thing, which is AVL delete? So for AVL delete also, you will be first doing BST delete and then balancing. So balancing is not going to cost you anything. I mean, it is just going to cost order of 1. So let's not worry about the balancing. For BST delete, you may take order of log n, right? I mean, this is actually order of height, but in case of AVL tree, the height is log n itself. So that's why you can say BST delete is order of log n, right? So suppose you want to delete some node which is not a leaf node or something like that. Suppose you want to delete this node. Okay, suppose you want to delete this node, then what you will be doing, since it is having both children, so you will be either replacing with this node, or you will be replacing with this node, right? So suppose you replace with one of the node. Suppose this is the AVL tree that you have, and you replace with one of the node. So once you replace with one of the node, what you are going to do, you are going to do balancing, because it is BST delete plus balancing. At what node you are going to do balancing? Once you delete this node, you are going to do balancing at this node, because you have actually deleted this node, right? So you can do BST delete plus balancing in AVL tree. So we have seen everything about the AVL tree. I have tried to make this AVL tree very intuitive, because these terms are very confusing. LR rotation, RR rotation, these are many different terms in the books and in every article that you see over the internet. But we have tried to make it very intuitive in terms of elbow and stick. So I hope that you have liked this topic too much, because now after teaching this elbow stick method, this topic has become my one of the favorite topic. So I hope you liked it, and yes, that is all about the AVL tree.